Okay, good afternoon all. First of all, welcome sir, Dr. G. Linendra Chaudhary garu. Sir, good afternoon.
Good afternoon, sir. Thank you.
Good afternoon. Welcome. And welcome to all my dear participants. Today is the last day, that is day 6 of our 6-day online Atal FDP. Sir, just raise a hand so that I will make you presenter, sir, to share the screen.
Yeah, sure.
Okay, sir. Yes, sir. Now you are a presenter. Please check your screen share option, sir, once. Dear participants, as I already requested you, you please join this meeting with your full name so that it will be convenient for us to mark your attendance. Sir, first slide is visible. Please change the slides. Linendra, sir.
Yeah. Is that okay?
His slides are changing, sir. Changing.
Okay.
Okay. Our co-coordinator, madam, will introduce you to the meeting, sir. First, after that, you can again share your PPT and you can continue the session, sir.
Okay. So now I will stop the sharing right now.
Yes, sir. Yes, sir.
Okay.
Arpita, ma'am.
Yes, sir.
Yeah, you can share your screen. Starting slides.
Yes, sir. Am I audible, sir?
Yes, ma'am.
Okay. Good afternoon, everyone. Good afternoon, sir.
Yeah.
It gives me great pleasure to welcome you all to the 6th day, that is the last day of AICT Atal sponsored FDP on advanced VLSI design and AI-enabled automation for the next generation semiconductor manufacturing. After a highly insightful and 5 engaging days of FDP, we look forward to continuing the same momentum with another enriching set of sessions today. We have with us distinguished speaker, Dr. G. Linendra Chaudhary, sir. I take the privilege of introducing Dr. G. Linendra Chaudhary, sir, to you. Dr. G. Linendra Chaudhary is an accomplished academician and researcher currently serving as an assistant professor in the Department of ECE at SRM University, AP. He holds a PhD in electrical engineering from the National Taipei University of Technology, Taiwan, with specialization in switched current circuits, delta sigma ADCs, signal conditioning circuits, and FPGA-based system design. He has held notable research positions, including a postdoctoral research associate role at Baylor University, USA, and has extensive teaching experience as an associate professor at the SESI Institute of Technology and Engineering. His research contributions are well recognized with publications in reputed journals such as IEEE Access, IEEE Sensors Journal, and IET Circuits, Devices and Systems. His areas of expertise include analog and mixed signal IC design, sensor interfaces, energy harvesting systems, and embedded VLSI design. He has collaborated on several international research projects in Taiwan and Korea and has secured funding for the design and fabrication of RF energy harvesting chips, Hall sensors, and predictive torque control systems. With a passion for innovation and academic excellence, he continues to drive impactful research while mentoring the next generation of engineers. Sir, we heartfully welcome you to this session. I request you to share the presentation and hand over the session, sir.
Is it audible?
Yes, sir.
Yeah, so thanks for the introduction, ma'am. So
Thank
this
you,
is Dr. Linendra, so assistant professor from SRM AP. Today I would like to give a talk on analog circuit optimization that's using the machine learning algorithms. So the agenda of the today presentation is the motivation for the analog circuit optimization. So that is why we need to go for this analog circuit optimization. So then we can see what are before going for the analog circuit optimizations. First, let us see what are the challenges in the analog circuit design. So thereafter, we can see what are the analog circuit optimization methods we have. So anyway, we have different optimization methods. So then we can go for the ML-based optimization. So with that ML-based optimization, we have several publications are there. So we can see those publications as a case studies. So then we can see the optimization methods and the trade-offs. So what are the trade-offs? So with these optimization methods, so finally we can go for the conclusion and key takeaways. So this is the agenda of the today's section. So let's go to the first one. It is a motivation for the analog circuit optimization. So as you know, so before going to the analog circuit optimization or analog circuits, so if you are consider the digital design, for the digital design, simply you are writing a code, so then it is automatically gives the layout and you no need to bother about anything. But when you are going for the analog design, so we have so many things we need to consider, like what is the gain of the circuit, what is the performance of the circuit, I mean the speed of the circuit, how much area it was taking, everything we need to consider. Okay, so that is now for the analog design. So first of all, we need to design from the transistor level. Okay, so then thereafter you can go for the layout. So that is layout versus schematic, DRC, and everything we are going. So anyway, while going for transistor level design, so first of all we need to consider the parameters, like are the parameters, or we can say the specifications, so that the circuit is meeting or not. So for that, we need to consider about the what are the different sizes of the transistors, how much bias current we need to give. So is there any need of like compensation capacitors or resistors are needed? So that's what we need to look at about these things. And these are the things must be done by only the manual. So we cannot do by the automatic. So then the thing is we can do some automatic optimization, like changing of these transistor sizes and changing of the bias currents, and we can do so automatically by using some machine learning algorithms. So for this machine learning algorithm, first of all, we need a information about the data. Like data means here it is what the circuit you are having, how the circuit is connected, right? So then what are the parameters we are looking for the circuit? So then what is the application of the circuit? Like depends upon the application, the parameters again is going to be changing. So then we are modeling the circuit like a surrogate model. So then we are going for the optimization, like which parameter we need. So according to that, we are going for the optimization by using some optimization algorithms. Okay. So this is like, suppose if I'm considered like a two-stage CMOS operational amplifier design. So now I am having a specifics like gain should be more than the 60 dB, and the unity gain bandwidth is like more than the 50 megahertz, and phase margin is about more than the 60 degrees, and I need a power like 1 megawatt. So these are the specifications I need to design this a simple two-stage CMOS operational amplifier design. Okay, so for that, if you are going for the a manual process, okay, if you are going for the manual process, so first of all, we are choosing the what the transistor W by L ratios at the input side. I mean, at the input differential pair. So then we are looking for the bias current. How much bias current is needed to get this required gain. So then we are looking for the whether this amplifier is stable or not. Suppose if the amplifier is not stable, so then we are providing some compensation capacitor. So between the stages to get a reasonable phase margin, as I said, like here it is more than the 60 degrees. So then we are going to simulate this circuit at different corners. Okay, so after simulation, now we are looking for the whether we are getting that required gain or not. Suppose if you are not getting the required gain or required this gain bandwidth, or if it is not stable, and finally we are looking for the power consumption also, right? So if these requirements are not meted, so then you are again redesign. Okay, so that is, I mean, either we are changing the W by L ratios and we are changing the bias currents. Okay, or we are looking for these capacitors. Okay, so that is now we are having these things we need to do repeatedly. Okay, so that is every time you need to change the W by L ratio. So then we are looking about the simulations and all. So that is we have a n number of iterations. Okay, we are having a n number of iterations for the SPICE simulations. Okay, so that is it will take definitely it will take the more time if I want to design a specific one. Okay, so and moreover, we are getting an errors like suppose if I'm doing the 4 times or 5 times, so to simulate this two-stage CMOS operational amplifier. So then I'm not looking about every time I'm not looking about whether this transistor is operated in saturation region or whether it is operated in non-saturation region. So we are not looking every time. Since so as a human being, we are always thought like, okay, this is fine, we can go like that. Okay, so that is sometimes you misleaded from the region of operation of the transistors, and sometimes we are not looking about the stability and all. So because if I am done more number of times, so definitely I'm irritated. So I just skip some of the things. So those are very much needed. Okay, so but after the simulation, if I feel like okay, this is fine. So then if I'm going for the tape out, so after the tape out, you will again measure the result. Okay, so then so definitely it is not going to meet the requirements. Okay, so that is again you need to go for the tape out. So for the tape out again, it will take 1 more 2 months or 3 months or 6 months. It depends upon the fab. So now going for the number of tape outs is not usually preferred because it is more cost, right? So these are the main problems so that are associated with the designing of this analog IC. Right. So then we are looking for the ML. Okay. So that is for this ML. So first of all, we need a data. Okay. So the data like so earlier maybe you may have seen the machine learning algorithms for some IoT applications or for data applications and that. Whereas here the data means so the data has to represent the circuit and their connections and their dimensions. Okay, and finally what are the circuit specifications we needed. Okay, that is the circuit specifications we are describing in terms of W by L ratios or the bias currents, or suppose if you are consider for the two-stage operational amplifier with Miller capacitance, we are considering this capacitance also, right? Okay, so that is we need the data. Okay, so then we are going for this circuit modeling. So that is we are going for the number of simulations. Okay, so which one is better? So that one is going to be predicted by this ML. Okay, so finally we are looking for the optimization. So that is which optimization algorithm we can go for, like We can go for the either Bayesian optimization or reinforcement learning or some other machine learning algorithms. So to get the required circuit specifications, right? Okay, so that is if I'm going for a traditional flow. Okay, so let us consider if I'm having the traditional flow. So now I'm going for the 20 to 30 times of iterations. Okay, so definitely it will take the weeks of time so to get what is the gain, what is the bandwidth, what is the stability, and you need to take the information about the each iteration, what is the gain of the circuit, what is the bandwidth of the circuit, and what is the stability of the circuit. I mean the phase matching. Okay, so that is you need to note down these 20 to 30 iterations of information, either on the paper or you can go for you can save the data. But if I'm going for the same circuit design, so by using the ML assisted flow, so now I can go for the generating. Now I can go for up to generate 500 training samples. Okay, so that is from the SPICE. So then you can go for the training the surrogate ML model. Okay, so then you can apply the Bayesian optimization. So instead of taking this design weeks, so it will take the hours. Okay, right? So that is now we are we can go for the time. I mean, the designing time will be reduced. Okay, if I'm going for the ML assisted flow. Okay, so anyway, earlier I was taking a two-stage operational amplifier. But if you are taking a circuit which is more than the 10,000 transistors or 15,000 transistors, so you cannot going to change every W by L ratios manually, and you cannot see the what is the circuit performance and all, right? So this is very difficult, right? Okay, so that is now that's why if I'm going for this challenges, if I'm looking for this, what are the challenges so that are associated in this analog circuit design. So the main challenge is we need to meet the required specification. That's it. Okay. So that specification is not only it is not same for the all the circuits. So some circuits may looking for the low power. Suppose if I'm looking for the amplifier, I'm looking for the gain. Okay, and the stability, right? So if I'm looking for the ADC, I'm looking for the what is that INL and DNL. If I'm going for the LDY, I'm looking for the what is the fusion current, what is the PSRR and all. Okay, so that is depends upon the circuit. So now anyway, so now the parameters are going to be changed. So now anyway, this is the analog design octagon. We can say it is. So every circuit, most of the circuits, you are looking for these are the parameters, like how much gain it is. So what is the supply voltage we needed? So what is the voltage swing we needed? Okay, how much delay it is? So what is the input impedance? What is the output impedance? How much power dissipation it is going to be going for that? So now what is the noise of the circuit? So these are the things we need to consider, but it is not mandatory for all the circuits. Okay. So that is for some circuits, I may look at about the only linearity and gain. And some circuits, I look at about the only input impedance and output impedance. And some circuits, I'm just look at about the what is the power dissipation, what is the voltage swing of the circuit. Only these things we are considered, right? Okay. So now if I'm considering why it is going to be like these parameters. Okay. So that is now anyway, you are dealing with only the analog. So first thing, it is analog. It is a continuous nature of the continuous nature. So that is the output value is completely, it depends upon the frequency, amplitude, and phase. Okay, so these are the parameters, so that is going to be affected. So suppose if there is any frequency depending elements are there, like if there is any capacitor or inductor it is there. So now the output is definitely going to be affected. Okay, so and second thing, it is non-linear behavior. Okay, so now the non-linear behavior, as you know, we are dealing with the only the semiconductor devices, as this MOSFET is one of the semiconductor device. So these semiconductor devices are non-linear devices. Okay, so that is the output and input relationship you have considered for the MOSFET. There is a square relationship, right? Okay, so there is a non-linear behavior. So now that is if I'm giving the input, so it is not going to be same like it is multiplied with some factor or not. So it is not the same. And we have a multiple performance factors are there. Like if you are consider there is a gain, there is a bandwidth, there is input impedance, there is a output impedance. Okay, and finally we are looking for the whether it is gives the low power or it is gives the high performance or not. Okay, and moreover now anyway these circuits are these designs are is going to be operated at different conditions. So now these different conditions may vary. I mean the transistor while we are going for the fabrication and all. So because of the process variations, if you are going for the simulation, it will give the one result. After the fabrication, it may not give the same result. Okay, after the result, you may not give the same result. So that is, the circuit simulations is fine. Now the post layout simulations is fine, but when you are going for the measurement of that chip, so definitely it is degraded. Okay, definitely it is going to be degraded with respect to that post layout simulations, right? So now here I'm considering a two-stage CMOS operational amplifier with the Miller capacitance. Okay, right. So here at the input side, now I'm having a differential pair. Okay, this is the differential pair. So that one is actually biased by a 2I current source. Okay, and you are having the two PMOSs. So that is the current mirrors. So these are acts as a current mirror loads. So this is the actual the first stage of the amplifier. Okay, so and you are having a second stage. Okay, this is the second stage. Okay, so now the second stage we are having the NMOS and PMOS transistor pair. So now it is going to be further amplified. Okay, and so now as the gain is increases, now there is going to be happening there is a instability of the circuit. So to avoid that, we are going for a one compensation capacitor. So that's why this is called Miller compensation capacitor. So that Miller compensation capacitor is connected in between the first stage and the second stage. Okay, and finally we are having a load capacitor here. So that is V load. Okay, so these are the circuits. So that is now the circuit we are having the PMOSs and NMOSs, and these may operate at different regions. Okay, so that is now if I'm changing this capacitance, I mean the Miller capacitance. Now what is the phase margin that is going to be affected? Suppose if I'm changing the differential pair W by L ratios, so what is the effect of the output? Suppose if the load capacitance is changes, then what is going to be happen? Okay, right? So these are things we need to consider, right? So that is now if I'm going for a thumb rule, now the parameters like if I'm considering the current, suppose if I'm considering this bias current, if I'm increasing this bias current, okay, so definitely the slew rate is improved, the gain bandwidth is increases, but the voltage gain and phase margin is going to be reduced for the circuit. Okay, for suppose if I'm going for this Miller compensation capacitance, now the slew rate is reduced. Okay, now the voltage gain is remain same, that the phase margin will be increased or gain bandwidth product is going to be decreases. Suppose if the width of the channel is increased, okay, so if the width of the channel is increases, now the voltage gain increases and gain bandwidth is increases. Now the phase margin is going to be decreased. Okay, so these are the parameters so that are going to be affected if I am changing the bias current, if I am changing the Miller capacitance, if I am changing the length of the channel, nothing but the W. Okay, right. So now I'm considering now this is op amp. So this op amp now I'm looking to use in a high speed data converter. So the data converter may be analog to digital converter or digital to analog converter. So let us consider I'm going to use this analog to digital converter. Okay, so now this analog to digital converter, most of the times, anyway, if you are going for the ADC, so you are always looking for the high resolutions as well as the high speeds. So that high resolution is completely depends upon the sample and hold circuits. Or if I am considering the flash type ADC, so it depends upon the number of comparator stages. Right. So that is the op amp plays a main important role in this analog to digital converter. So then what you are looking from this ADC? I mean, what you are looking for this op amp for this ADC? So that is now we are looking for the first thing, it is high slew rate I needed. high gain I needed, okay, and good stability, and definitely a low power consumption. So for the applications of only the portable devices, right? So that is if I'm having the high slew rate, so definitely in the sample and hold circuit, the charging and discharging of the capacitors is going to be very fast. That means it is fastly going to be responded, right? So suppose if I'm having the high gain, so this high gain definitely improves the resolution of the ADC, whereas the good stability. So if you are having the stability, so the feedback loop oscillations definitely it is going to be avoided. Okay, so these are the parameters I'm looking for this. Okay, so that is if I'm looking for these parameters. Now what I am thinking I need a high slew rate and a large gain bandwidth. So then I'm trying to increase the bias current. Okay, so but the problem is now there is a lower gain and a higher power consumption will be happen. So because now if the bias current is increases, okay, so the higher gain will be higher power consumption will be there, right? So now I'm looking for the another option is increasing the compensation capacitor. Suppose if I'm increasing the compensation capacitor, like now I'm getting the more stable operation. But on the other side, we are having the lower slew rate and gain bandwidth. Suppose if I'm increasing the device size, okay, if I'm increasing the device size like W, so then you may have the better transconductance, so that is GM is good. So then the gain is nothing but GM into R naught. So the gain is improved. If the gain is improved, the resolution is going to be better. But on the other side, you may have the problem is definitely if the W is increases, so you may have the large parasites are going to be happening. Okay, so if the width of the channel is increased, now the transistor size is also increases, so it may lead to the larger area. Okay, so it may leads to the larger area. So these are the things. So that is now I'm looking for an op-amp for this high-speed data converter. Okay, so which I needed like high slew rate, high gain, and good stability and low power. So, but it is not going to be happen with this either current or compensation capacitor or W. So we need to go for the trade of these three parameters. So such that I need to meet the requirement. Okay, requirement for this ADC. Okay, but if I'm consider the same op-amp for the another different applications, okay, so that application may not be needed a high slew rate. That may not be needed a high slew rate. Okay, so there is depends upon the application. Okay, so the circuit dimensions are going to be affected, right? So now these are the 1 minute. Yeah, these are the analog circuit optimization methods. So that is so in order to optimize these parameters, whether I need to change the current, okay, I mean the bias current, or I need to change this length of the channel, right? So these parameters, how we can optimize these parameters. Okay, for that optimization, so then we can go for different optimization methods. One is based on evaluation. So that is based on evaluation is you can take the pen and paper. Okay, so you can write the transistor model, each transistor model. So then you are going to evaluate what is the gain, what is the bandwidth and all, what is the slew rate and all. Okay, whereas in the simulation method, simply you are connecting the same op-amp design. I mean the two-stage op-amp. So then we are going for the number of simulations like trial and error method without having the knowledge of how the circuit is going to be behave if the W is increased or if the bias is increased. Okay, so that is without the knowledge. Okay, whereas on the whereas we are having the one more based on the problem type. So in the problem type now we are having the gain and bandwidth. So now if I'm looking for the only the one parameter, it is gain. Or if I'm going for the multiple parameters like gain, bandwidth, slew rate and all. Okay, so that is we can go for the either single or a multi-objective parameters. Okay, so and whereas the another it is like a constraint. So like I need a constraint is for this circuit I need a 40 dB. I need a phase margin should be 60. That's it. This is the constraint. So these are comes to the based on the problem type. Okay, whereas based on the optimization algorithm, so we have different kinds of algorithms like optimization algorithms. One is a deterministic. Okay, so where we are using the gradient method, whereas another one is stochastic. So where you are using particle swarm optimization and another genetic algorithms. And the last one, it is ML based. So where you are using the Bayesian optimization and reinforcement learning or surrogate models. Okay, so these are the optimization models. Okay, so optimization methods. So let's see with an example each optimization method. So finally we can go for that ML based optimization, right? So now the first of all based on the evaluation. So this based on the evaluation basically it is an analytical model. Okay, so now you are having the equation method and simulation method. So now if I'm considering the equation method, now in the equation method, what we will do is we are considering the mathematical model of the each transistor, and we are going for the small signal analysis, right? So there we are considering the equations. We are writing the equations like in terms of W by L ratios, what are the bias currents. So in order to get this, in order to get the performance parameters like what the gain you will get it, what the bandwidth you will get it, what the power consumption you are getting. Okay, so that is by optimizing these equations or by solving these equations, we are trying to meet the specifications, right? Okay, so let us consider the same example like a two-stage operational amplifier. Okay, so now I'm having the three parameters. One is a DC gain, and another one is a unity gain bandwidth, and third one is a slew rate. Okay, first of all, if you are consider this DC gain, okay, here I'm having the two stages. One stage gain it is GM1 RO1, and another stage having a gain of GM2 RO2. So that is overall gain is GM1 and RO1, GM2 RO2. Whereas unity gain bandwidth it is UGB, it is like GM1 by 2 pi CC, that is Miller compensation. And finally, the slew rate is like it completely depends upon the bias current and Miller compensation, that is I bias by CC. Okay, so now these are the three parameters I am looking for the optimization. So then what I need to do, I just looking about what is the value of W by L, right? And what is the bias current? Okay, so from that you are going to directly compute what the gain, bandwidth, and slew rate. Suppose if the gain is less, okay. So if the gain is less, now the gain is completely depends upon GM1, RO1. Okay, so that is we are trying to increase the RO1. Okay, we are trying to increase the RO1. How we can increase the RO1? Simply increasing the length of the channel, right? So that is the W is increases so that the gain will be increased. Okay, so then we are looking for the slew rate. Okay, now if the slew rate is low, now the slew rate is anyway directly proportional to the bias current, right? Now we are trying to increase the bias current. But on this other side, if the bias current is increases, definitely the power consumption is more. So that is the problem here. Okay, right? But now in this equation method, you are directly consider, okay, so the gain, unity gain bandwidth, and slew rate. So these are only the consider directly are consider the parameters, okay, but you are not considering about in detail about the parasitics and the process variations, how non-linear it is, and we are also not consider the like second order effects. Okay, so that is if I'm going for at higher frequencies, so definitely the second order effects comes into the picture, right? Okay, so that is the main limitation in this equation method. Okay, whereas the simulation method, so in the simulation method, what I'm doing is I'm using some simulation simulators like SPICE or Spectra or H-SPICE simulators. So where we are going for the transistor level models, simply using these B-SIMs. Okay, we are trying to capture what are the non-linearities, parasitics, and process effects. Okay, so then we are optimizing the number of times. Okay, that is we are changing the W by L ratios, bias currents, capacitance, just by trial and error method without any knowledge. Okay, without any knowledge. Okay, right. Without any knowledge, we will do this. generally what the basic analog design engineer will do is like based on evaluation, like he will first of all he will do the equation method, then he will go for the simulation method. Okay, so now for this, what we will do, suppose if I'm considering the same op-amp example, okay, so I need a 60 dB of gain, and the phase margin should be more than the 60 degrees, and it has to consume the minimum power. So these are the requirements. Okay, these are the client requirements. Okay, so now what we will do, simply we are going for the transistor level schematic design, either in Spice or any other platform. So then we are trying to measure the gain, bandwidth, and what is the phase margin from the AC analysis. And from the transistor analysis, transient analysis, so we are trying to measure the slew rate. Okay, so now we are trying to adjust these parameters. Okay, so that is W by L ratios, the bias currents. We are trying to adjust these parameters, and we are trying to get this gain and phase margin. So without knowing those relationships and all, we are just try to do as like a trial and error method. Okay, so now if I'm consider this one, like if, as I said, it is a trial and error method. If you are going for the number of times, so that is there are hundreds of simulations it may take. Suppose if you are lucky, you may take maybe in the second simulation or third simulation itself, right? So that is from these you may not know what is the direct relationship between the output parameter, okay, I mean output performance metric as well as the input parameters. Okay, so that is there is no relationships. Okay, but this is if it is a simple design, I mean if you are having the design hardly having the 4 or 5 transistors, it is fine. 4 or 5 components, it's fine. Suppose if you are having the 100 transistors, so definitely it is not going to be workout. Okay, definitely it is not going to be a workout, right? So this is a simulation method. Okay, so now if I'm going for the problem type, okay, based on the problem type, so now we can go for the single or multi-objective. I mean, if it is a single objective, okay, that means I'm going to consider only gain. Okay, I'm considering only for the slew rate. Okay, like that. So there is depends upon my application. So if I need only high speed, I'm not bothered about the gain, and I'm not bothered about the power consumption and all. So then simply I can go for the only the slew rate. That is a single objective. Whereas the multi-objective, so now we are going for the several parameters. You are considering the gain, you are considering the bandwidth, you are considering the power, and you are also considering the slew rate, right? So these are the different parameters we are considered in the multi-objective. Okay, so now in the multi-objective case, you are simply lie on a Pareto frontener. So we can see what is that. So that one gives a best trade-offs, which one is better and which one is not. Okay. Okay, so this is the thing. Now, if I'm going for the single objective, okay, so let us consider same op-amp design. Now I need a maximum gain. Okay, if I need a maximum gain, I'm trying to increase the length of the channel. Okay, that is output gain is equal to GM into R0. Okay, now I am trying to increase the R0 by increasing the channel length. Okay, but on the gain improves, but opposite side, the speed is going to be reduced. Okay, so that is now I'm increasing the channel length. So if I'm increasing the channel length, so definitely the gain, okay, the intrinsic gain, it is going to be like GM into R0. It is going to be increases. But if the gain is, if the channel length is increased, so definitely the parasitic capacitance C, it is going to be increased. Okay, so if the parasitic capacitance is increases, definitely the bandwidth is reduced, and further it slow down the circuit. Okay, so now this is like if I'm increasing the length of the transistor, now the drain current it is decreases. Okay, now the drain current is decreases. So if the drain current is decreases, so then the R0 will be increased. So now the voltage gain anyway it is going to be increased, right? Okay, so now if I'm considering this is single objective, now I'm considering the maximum gain. Now what is the speed it is? Okay, so now you can see this orange line. So now this gain is increasing. So if the gain is increases, now what about the speed? Speed is decreased. So anyway, it is not a linear relationship. So definitely this is a non-linear device. All the semiconductor devices are processed in non-linear, right? So now this is a exponential decay. We can consider as this is an exponential increase, right? So this is because now if I'm increasing the length of the channel, okay, if I'm increasing the length of the channel, R naught will be increases. Now the gain is increasing. So now what about the on the other side due to the parasitics? Now the speed is decreased. So then I am looking for a something like a trade-off region. Okay, so where the speed and gain, I'm getting a better values. Okay, so that is always a trade-off. You are looking for the always a trade-off, right? So now I'm looking next. If I'm going for the earlier case, if I'm looking for the only the gain, okay, then it is a single objective. Now, if I'm going for the more than one parameter, so then you are going for a multi-objective problem. It is. So that is what is the maximum gain. Okay, I need a maximum gain bandwidth and minimize the power. Okay, so in order to do this, so then I'm just try to search the algorithms. Okay, so to get the transistor size combinations. So now these searching algorithms like genetic algorithms or gradient descent algorithms. Okay, so now what we will do it is, so we are trying to Pareto frontliner is plotted. So now each point as a one design. So the each paraset is, you have a, what is the improvement it is. Okay, now we are looking for the Pareto optimal set. Okay, what the optimal set for the design. Okay, so now this is, now this is a candidate design. So these are the oranges are, these are the candidate designs are there. Okay, so now I'm going for the optimal design. So this is the optimal design one. Okay, this is another, and this is another. Okay, so for this, the power consumption is 0.06. Okay, the gain bandwidth product is more. Okay, whereas for this, the power consumption is less, the gain bandwidth product is medium. So then we are looking for a region like this one. Okay, we are looking for a region like this one. So that is earlier we are consider if I'm increasing the length of the channel, what is the gain? So now if I'm increasing the length of the channel, now what is the gain bandwidth? What is the power consumption? What is the gain also? So we are considering all these three parameters in this multi-objective. Okay, in this multi-objective. Okay, so and another one, it is in the problem type. So now I have a certain constraint. Okay, that is constraint based. So now that is in this constraint. So you may not say it is only the one objective or two objectives. So it's completely depends upon the application. Let us consider if I'm having the one or more objectives. Okay, one or more objectives. Okay, so that is, so to meet some X value, how to optimize the Y value. That's what we need to do this one. Okay, so now this is the constraint. Okay, this is the simple constraint. Okay, so the constraint is I need a gain is more than the 40 dB and the phase margin is more than the 60 degrees. So now I want to minimize this power. Okay, minimize this power. Okay, if I want to minimize this power, so then what are the possibility things we need to consider? Okay, considering the gain and phase margin also. Okay, considering the gain and phase margin also. Right. Okay, so that is now I'm looking for the gain is more than the 40 dB and phase margin is 60 degrees. This is the constraint. So now I'm going for the first candidate. Okay, because here one simulation we are considering as one candidate. First candidate, now the gain is 38 and phase margin is 70 and power consumption is less. Okay, so now here the power consumption and power phase margin is fine. Okay, but the second candidate, I mean second simulation, now it gives the gain, it is 45, phase margin is 55 and power is 0.3 milliwatts. Okay, so now in this case phase margin is not up to the mark. Then the third case, it is fine, 50, 65.5. Okay, that is all the parameters is fine. But D and E, okay, D and E candidates will give the good phase margin as good gain, but the power is like, I'm looking for the low power that should be like less than the, I'm considering less than the 0.7 or 0.8. But here I'm getting the 0.8 and 1.2 volts. Okay, so then I can choose only the design which is having the candidate C. Okay, we can say it is candidate C. Now all these three parameters are optimized. Okay, this is my constraint. Okay, whereas in the another constraint, I may have like only the candidate B is enough. Like I need a good gain and less power consumption. So then I can go for the candidate B. Okay, so whereas another constraint is like I need a gain is more than 70 dB and phase margin is more than 80. Okay, so I'm not bothered about the power consumption. Then I can go for the candidates. Okay, so that is now you may have the constraint optimization. So and you are also having the multi-objective optimization. So both are comes to the problem type. So now in the constraint optimization, so design must work. Okay, that is first we are looking for the specifications, then we are going for the optimize. Okay, whereas the multi-objective optimization, we are going for the n number of simulations, and we can see the all the possibilities. From the all those possibilities, we just look at about which one is a better one. Okay, which one is a better one, right? So that is in the multi-objective, we are not going to look at about the spec. Okay, whereas in the constraint type, first we will look about the specifications, I mean spec. So then we are going for the optimization, right? Okay, so then based on the optimization algorithms, okay, so we have a different optimization algorithms like, right? So one is a deterministic. So in the deterministic method, so what we will do is we will go for the some gradient based methods. Okay, we will go for the some gradient based methods. Okay, so that is by using some slope of equations. Now we will see what the improvement of that parameter. Okay, so that is we are directly looking about what the relationship and all. Okay, let us consider. So now I'm having again a simple like minimize the power and gain should be 40. So now I'm looking for something like Newton-Raphson gradient based optimization. Now in this optimization, now the algorithm is going to be compute what the gain and power. Okay, what the gain and power with respect to the transistor sizes as well as the biasing. Okay, so now this this optimization method, what we will do it is what it is doing it is continuously changing the adjustment of the sizes. Okay, and check that whether we are getting the same the required gain with minimum power or not. Okay, so this is what we will do in the deterministic. Whereas stochastic, in the stochastic, so there in the deterministic, like we will start from the 1, 2, 3, like 100 simulations we will go. Okay, so where you got it, then you will do it. So whereas in the stochastic, you will go for the random set. Okay, so that is instead of gradients like increasing the 1, 1, 1, 1, 1 like that. So here we will go for this some random values. So that is random values, random values of W by L and the random values of the biasing current. Okay, those random values. So you are trying to find out the global optima. Okay, sometimes now the stochastic it is going to be, sometimes it may be advantage because the probability of getting the easier, the set of parameters, maybe you will get in a less time. Sometimes it may take more time. Okay, it's completely depends upon you are taking the randomized, right? So that's why it will take, sometimes it will take more time, sometimes it will take less time. Okay, right. Okay, so now generally for this, what we will do is for this stochastic, we will go for some genetic algorithms, simulated annealing, or particle swarm optimization. Okay, so now if I'm considering this genetic algorithm, so first of all, first it randomly generates the transistor sizes. Okay, depends upon the number of transistors, the population. Okay, it will randomly generate the transistor sizes. Now it will check the gain for each set. Okay, so there is it checks the power and the gain. Okay, so now this is continuously repeating. Okay, so suppose first it will select, then it will cross over checking that parameters. So if it is fine, then it is exits. Suppose if it is not fine, then it will mute that or mutation that that set. So then it going for the next set. Okay, this is a try to process again. Okay, so now the final population we will give the apparent or friend. Okay, so these are the things. Okay, so now if you are going for this ML based. Okay, now in the ML based, what we will do is like we will go for a Bayesian optimization or a reinforcement learning algorithms. We have other algorithms also. So first of all, here we will train the ML model on a SPICE data to predict the circuit performance. Then we will go for the RL. Okay, then we will go for the RL to guide the transistor sizes to get the minimum power. Okay, so in this case, we cannot go for more number of simulations. Okay, so anyway, we can go for the less number of simulations. Okay, but before that, but before that, we need something training data. Okay, so we need some training data. Okay, okay. So that is first of all, it learns from the data. Then it predicts the complex relations. Okay, then handles the high dimensional problems. So then work with the simulations. Okay, so now where we are going to fit this one. So first of all, we are taking the circuit. Okay, then we are considering in the circuit and their parameters and everything as one data. Then we are applying the ML, okay, ML algorithms. Then we will get the optimized circuit. Okay, so that is from the circuit to data. So again, we are going to going for some neural networks or some neural networks to represent these things. Okay, data. So then we are going for the ML to optimize. Okay, to optimize. Okay, right. So that is in the ML based optimization. Okay, now let's come to the ML based optimization. First of all, we are considering the circuit modeling and simulation. So now in the circuit modeling and simulation, either we can use something like ngSpice, LTSpice, or Spectra. Okay, so to get that circuit information. Okay, circuit information. Suppose if you are considering the ngSpice or LTSpice, we are writing a code like by using the something nodes, by representing the nodes. So that nodes information and the connectivity information, you have one file. Okay, so that file. Okay, so then we are trying to get that data set generation. So that is in the data set generation, what we will do is we will try to get that what the resistance, capacitance values, and the W by L ratios. So in terms of the gain, delay, and power. Okay, and these data sets are saved in a Python scripts. Okay, so then we will go for the machine learning optimization. Okay, so in the machine learning optimization, we are trying to predict the what is the performance of the circuit from the model. Okay, so finally we will go for the automation framework. So that is now it is going to checking the different parameters, run the SPICE simulations, and you will get a performance circuit with those dimensions of that circuit. Okay, right. So now this is like ML optimization. Now I'm going for the analog circuit optimizer here. So for that, first of all, we need a circuit specifications we need. Okay, circuit specifications we needed. So from the circuit specifications, so we are trained. Okay, we are trained. Okay, we are trained those circuit specifications. Okay, so if the circuit variables are, if it is yes, so then the model is finalized, then the circuit is optimized. Suppose if it is no, then we go for the SPICE simulations and we will apply the algorithms. So from the SPICE simulation results, we will apply the optimization algorithms. Then again, you are verifying the model. Then we are going for the optimization. So that is, we are having the simulation as well as the optimized algorithm for every case. Okay. So these are the machine learning optimization algorithms for different analog circuits. Okay. So that is, if I'm consider the LDO. Okay, for the LDO, if I want to apply the ML algorithms, now I can look at about the improvement of this power supply rejection ratio, improvement of this load regulation, and how much current we can minimize, I mean the quiescent current. Suppose if I am considered the oscillator, so definitely we are looking about the frequency stability and how to minimize this phase noise. Suppose if I am going for the amplifier, so what is the maximum gain? What is the bandwidth I can get it? So how much linear it is? How we can reduce the power consumption? And finally, if I'm going with the filter, so that is we will look at about what the cutoff frequency, how we can sharpen those sharpen that Q factor so that the selectivity is good. So the insertion loss. So these are the parameters for the each circuits. I mean, for the different circuits, you may have the different parameters, right? Okay, right. Okay, so for that, in order to evaluate that one, okay, so we need some evaluation metrics. So these evaluation metrics are, so one is a mean square error. So for the mean square error, it is actually gives the difference between the predicted and true values. So that low mean square error will gives a better model accuracy. Okay, whereas the quotient of the determination, so that is R square. We can say it is R square. So this one actually indicates how much of the variance in the circuit performance. Okay, so if it is good, if it is 1 means it is perfect fit. If it is 0 means no predictive. Okay, so that is you can I generally we will expect in between the 0 to 1. Okay, this R square value. Okay, whereas Pareto front coverage. So now in the Pareto front coverage, now it is going to be comparing different parameters, gain versus power, speed versus area. Okay, with the SPICE results. So now the this fraction of this Pareto actually we will get it from the ML. Okay. So now this is the model evaluation metrics. So now I'm just going for the different one is NN, GPR, swarm optimization, linear. So these are the different. So now you can see that MSC value is we are always looking for the low value, right? So that is a linear regression. It is not good for MSC, but in neural networks it is good. Okay. Whereas here it is I mean, R square, it is almost like it is good for NN. Okay, this is actually simulated for one design. Okay, this is simulated for one design. This may not be true for the all the designs. Okay, so this is the accuracy, and this is the Pareto front coverage. So that is SPICE versus simulation, ML. So now the predictors you are getting like this red color. It is like ML algorithms. Whereas this is the SPICE Pareto, I mean the SPICE simulations. So this is the predicted value. So this is the closed value. Okay, so now in this ML based optimization, so again we can go for the different algorithms. One is supervised learning. So that is it is only for the performance modeling. Whereas unsupervised learning, so this is for design exploration, design space exploration. Whereas the reinforcement algorithm, this is for adaptive optimization. Whereas the hybrid techniques we are going, so this is it is looking for the reducing the simulation cost. Okay, so in the supervised learning, so where we are considering only the inputs and outputs. Okay, we are directly mapping. Okay, so the outputs in terms of the parameters. Like if I'm having the gain, what the gain with relationship to the WBL, bias current and compensation capacitor. Okay, right? So now it is going to be predicted. Okay, it is going to be predicted that information. So within the small stipulated time. Okay, so this is the schematic. Okay, this is the schematic. This schematic having several components. Okay, so these several components, actually this is the connection. From the connection we will apply the ML model. So then we will go for the simulation and validation. Okay, so that is for that. First of all, what we will do is, first of all we will select the circuit parameters. So then we will check it that whether the changing the parameters within the range or not. So then we will set one of the parameter. Okay, we are going to select one of the parameters. Then we are calculating the performance metrics. Okay, so if this performance matrix is fine, so then it is these are the parameters set. So with these parameters we are getting this performance. Suppose if it is not fine, so then we will go for again selecting the another parameter. Okay, so this is the thing. Okay, so that is now if I'm consider this one. First, what we will do. Okay, so the step one, it is like the data collection. From the data collection, we are going to vary the circuit parameters and we are trying to record these performance metrics. Okay, so this is the label data set. So that is these are the W/L ratios. These are the output parameters we are getting. Okay, so then we are going to train this model to the neural network. Okay, so once if it is done, okay, so then we are trying to optimize this output point, whether you are getting the maximum gain, maximum bandwidth, or minimum power or not. Okay, so it is like continuous. Okay, so that is now in this case, instead of like going for the n number of SPICE simulations, so within less than 50 simulations, you will get a better option here. Okay, whereas unsupervised learning, in this unsupervised learning, we are trying to look at about hidden data. Okay, some hidden data. So now in this hidden data, we are trying to go for the thousands of R and C values, like you can say parasitics. So from that, we are trying to separate. So which one it is. Okay, for suppose if I am considering a filter, whether it is a low pass filter or a high pass filter or a band pass filter. Okay, so these are further simplify using the PCA. Okay, so let us consider if I'm going for the analog filter design. Okay, so first of all, we are trying to randomly sweep the resistor values and capacitor values for the RC circuit. Okay, so then we are going to collect thousands of circuit configurations. So now we are trying to give, okay, these simulations belongs to the low pass filter, and these simulations we are going to the high pass filter. So that is we are going for the clustering. Okay, clustering. So that is K-means algorithm you are going to use. So these are the simulation results actually. So these are the simulation results. So from the simulation results, now I'm going to separate. So one blue color, it is like low pass filter, and red color, it is like high pass, and green color is like a band pass filter. Okay, so that is we are clustering. So from those clusters, okay, so now this clustering can be done by using this principal component analysis. That is a different story again. So that is in this principal component analysis, we are trying to divide that high dimensional data into 2 or 3 principal components. Like this is category A, category B, category C, like low pass filter, high pass filter, and band pass filter. Okay, whereas the reinforcement learning, so this is something interesting. It is okay for the reinforcement learning. Now actually it is a sequential decision process. Okay, so sequential decision process. So here also we will do number of times. Okay, for example, if I'm taking this one, so this is the actual LDO here. Okay, now this LDO, we are giving the circuit simulations. So then we are trying to find out the reward function. So then if it is correct, so then we are going for this one. Okay, so that is, first of all, in order to do this one, first of all, we are representing the circuit as a graph. Okay, so that is actually, this is the circuit. So this circuit actually we are representing like these are the transistors. So these are the voltage source, these are the resistor, these are the capacitors. Okay, and we are giving the paths also, paths information also. What the small signal path, I mean AC, and what the DC signal path. So those things also we are trying to implement this one. Okay, so that is, we are simply representing the circuit as a graph. Okay, so for that, we will go for some graph convolution networks, or we can go for the another convolution networks also. That is ANN or different. Okay, so then this one is given to the a SPI simulator. So that is, this netlist is given to a SPI simulator, where we are trying to perform this. We are trying to know the PSRR, I mean phase margin, low power consumption. So this is actually LDO. So that's why we are looking for only these parameters. Okay, then we are trying to get the information about the reward. I mean, after the simulation results, so we will check the what the reward function it is. So if it is fine, so then we will go for it. Suppose if it is not fine, so then we will go for this agent. So that is agent critic model. Okay, so now in the agent critic model, so now again we are having the actor and critic, whereas the actor is going to be suggest what is the new circuit parameters. Then in the critic, now the evaluation gives the what is the expected reward. I mean, what is the predicted one. So, okay, so together we are trying to find that one. Okay, this is a continuous loop. Okay, this is a continuous loop. We are trying to find out this one. Yeah, any queries, please?
Sir, no, sir, it's some disturbance. You please continue. Disturbance of their mic.
Okay, fine. Yeah, finally it is a hybrid technique. So in the hybrid techniques methods, actually this is combining strength of all the multiple machine learning algorithms. So whereas that is unsupervised, supervised, as well as the reinforcement learning and Bayesian optimization we are going for. So now let us go with one example like, so now, first of all, here the problem is like which parameters we are looking for it. Okay, that is for one circuit, you may have the 20 parameters. So out of those 20 parameters, so I can go for only 2 or 3 parameters or 4 parameters maximum. So that is first, the design parameters are, first of all, it is confined. I mean, it is reduced. Okay, so then we are looking for the design. Okay, so that is, in this case, if the number of design parameters are reduced, okay, if the number of design parameters are specifications are reduced, so then the time for execution is also less. Okay, and second thing, it is like some of the parameters, like maybe some transistor parameters are there. So let us consider I'm having 10 transistors in my design. Out of 10 transistors, I can, some of the transistors may not affect the output performance. I mean, some of them may be affected the gain, and some of them may not be affected the gain. Okay, right? So those things we can avoid. Okay, those things we can avoid. So that is, we are trying to reduce the input parameters. I mean, the number of transistor widths and lengths ratios, or bias currents, or capacitor sizes. And on the other side also, we are trying to reduce the output spec. Okay, output spec. Okay, so that is, we are trying to like segregate all these things, and we are trying to reduce the number of those parameters. Okay, that's what it is, a dimensionality reduction. Okay, so then we are going for the neural networks. So this neural network is a supervised learning. So this is the fast surrogate modeling. So now in this, what we will do is we will try to consider the inputs and outputs. Okay, so now it is going to predict the performance. So in milliseconds. Okay, in milliseconds. Right. Okay, so then we are going to apply the Bayesian optimization or reinforcement learning. Okay, so that is the fine tuning of these parameters. So to get the reward functions. Okay, right. So let us consider now I'm having the gain so and so, bandwidth so and power is less than 200 microwatts. Okay, so now actually I'm having the 20 parameters. Now it reduces to the 3 parameters. Okay, so now instead of going for the 1,000 simulations, I can go for the tens of simulations only. Okay, so from that now, finally, we are going to apply the algorithm. Okay, Bayesian optimization, which one is gives the better promising one. Okay, so these are the ML optimization algorithms. Now, if you are going for these case studies, okay, the case studies of this ML. So now this is one is PSO, particle swarm optimization. It is. Now you can see the figure A. Okay, this is the PSO. Now it considers the all the parameters W1, W3, 5, 6, 7, and I bias. Okay, this is the NG SPI circuit with these dimensions. Okay, from these dimensions, if you are going for the DC analysis, AC analysis, and noise analysis, so now you are going to check, okay, whether the required spec meted or not. So if it is meted, then it is pass. So suppose if it is not meted, then we are going for again optimization. Okay, so now in the optimization, okay, what we will do it is we are trying to give the all the parameters. Now we are trying to check that length and width ratios. Now this, if this is fine in one platform, I mean in MATLAB, so then we are trying to give this length and widths, and we are trying to get these results. In another platform is like CAD tools, like I'm using the Cadence here. Okay, this is the operational amplifier. So this is a MOGA actually algorithm. It is okay. So and this is the proposed flow chart for this design. Okay, this is one case studies, and this is another. This is where we are using the ANN network model. Now we are giving the impact and polynomial features. These are the some hidden layers. It is. These are the design variables. It is. So first of all, we are giving the DC gain, current, gain bandwidth, and different parameters. Now we are trying to check the width and lengths. So we are not bothered about these hidden layers and all. Okay, so for that, what we will do, first of all, we are having the data. Okay, so then then we are getting the information. Okay, information using this NN. Okay, so then it is optimized using the PSO. So then finally you will get the optimized result. Okay, finally we will get the optimized result. So this is the optimal circuit topology for this angel. Okay, so this is one of the paper. Okay, so here it is circuit. The resistors are there. Now this is T2 and this is T3 and this is T0. So these are the different configurations of these circuits. So these different configurations are, I'm representing, this is one model. This is T2 is another model. And these models are given to the optimization. These models are given to the optimization. Now you can see in this model, okay, so this is one NN model. So there is a green color. Okay, whereas here there is a red color here. So that is, these are passed, whereas these are again going for the training. Okay, these are again going for the training. Okay, so in this way now we are trying to optimize this one. Okay, and this is the third case study where we are having like as I said, this is the case study related to the like hybrid learning. Okay, so in this hybrid learning, so we are trying to get the entire circuit information. So then we are trying to classify those circuits. So that is which transistors are give the slew rate, and which transistors will give the gain, and which transistors will give the like bandwidth. Okay, I mean which transistors affect those bandwidth, which transistors affect those gain and all. We will segregate those things. So that is classifying those things as a circuit 1, circuit 2, and circuit 3. Okay, so then we are trying to find out which side it is good and which one is not. Okay, I mean different circuit for the different parameters. Okay, so that is first extracted, then we are applying the algorithm, then we are trying to get the predicted values. Okay, these are the case studies. Okay, so finally, if I'm going for this optimization methods, what are the optimization methods and the trade-offs? So we have a like different optimization methods as we discussed. One is the analytical method, simulation method, stochastic and heuristic method, ML based method. So in the analytical method, so it is like using the equations from the small signal model we are going to calculate. Whereas the simulation method, we are using the something spice-based simulations, so that is DC analysis, AC analysis, transient analysis. Whereas stochastic, we are looking for the algorithms like genetic algorithms, particle swarm particle swarm optimization algorithm like that. Whereas ML based, so we are going for the data driven. Okay, so that is by using the neural networks or GNNs or reinforcement learning algorithms. If I'm considering the advantages, okay, so the analytical model method, it is we can estimate it easily. Okay, so that is okay. So but in simulation method, you will get something like, yes, if the simulation is good, so then we can go for the industry. I mean, the trustworthy for the industry. Whereas the stochastic, so we can go for a like we are going for the single objective or multi objective, right? So that is, if I'm going for the multi objective, this is something, it is fine. Okay, but it will go for the either random based or gradient based, right? So, but it is not suitable for all the cases. Whereas the ML based, first of all, we are segregating something, right? Okay, so that is, you may have the fast interference, scalable, and handle complex topologies. Okay, so if I'm considering the use cases, so now the first order design, it is simple. Okay, so because we are not considering the second order effects in that. Okay, whereas in the simulation, we can go for the verification and fine tuning is fine. Okay, so but stochastic and heuristic, it is like if you want to explore the design space, like if I'm increasing the 1%, 2%, or if I'm randomly increasing, what is going to be happen, right? So that one we can go it. And the ML based, like in the ML based, we can go for the fast optimization and transfer across the topologies. Okay, so these are the optimization methods and the trade-offs. Okay, so now finally, I just want to conclude this session. Like so now there is a analog design. Okay, so we are looking for the automation, like we are trying to avoid the number of iterative simulations, right? Okay, so that is the ML is like gives a better, I mean, try to reduce the number of simulations. Okay, and if I'm considering these surrogate models, okay, these surrogate models actually like a game changers. Okay, so it is like instantly it checks the the spice simulations and gives the a better results. Okay, so finally, if I'm looking for the a toolkit, so there is no like a simple toolkit for the ML algorithms. Like one algorithm may be suited for one, another algorithm may be suited for another. Okay, that is it's play a different and the complementary roles in optimization flow. Okay, so now if you want to work out on it, so what are the things you need to know? So that is, first of all, the circuit simulator, like a simple ngSpice or LTSpice. So anyway, all these are open source and free. Okay. Okay. So then you need to know the programming language Python. Okay. So either by Jupyter Notebook, I highly recommend it. And we need something, some Python libraries like NumPy and Pandas. So for data handling and manipulations, and MATLAB, Plotlib, and Seaborn. So this is for the visualization and plotting, and Skykit. So this is for regression models. Whereas PySpice and LTSpice Python libraries, actually these are for control your spice simulations directly from the Python script. Okay, so these are the key take. I mean, if you want to work on this field, analog circuit optimization, so then we can go for these things. Okay. And one more thing I just want to address, it is like, yeah, there is a EDA tool. Okay, so EDA tool, just want to share it once. Yeah, this is EDA tool. Actually, Synopsys 1 year back recently given this full stack AI driven EDS suite. It is okay. So this is the AI driven EDS suite. So this is from the manufacturing, testing, implementation, verification. So at all the stages, okay. So they are you can go for the AI-driven optimization. Okay, you can go for the AI-driven optimization. So there we are having the AI-driven optimization. So where we can go for the design space optimization by using DSO.ai. Okay, and verification space using the VSO.ai. This is another. Okay, so AI target simulations are automated. And TSO.ai. This is optimum pattern count achieving. Okay, so which one gives the better results? So that's what we can see. And Synopsys ASO.ai. This is another. There we can go for the multi-objective optimization and ML driven layout also. Okay, actually up to now I just discussed only the circuit design, not about the layout. This is Synopsys DA. Okay, this is design analytics. Okay, so this tool is available. Okay, so now this tool is just simply collects, detects the data and analyze, now predicts and automate. Okay, this is what. Okay, so this tool is available. So either if you want to go for open source, so you can go for this either Python, or simply you are also can go with MATLAB also. MATLAB is also you can optimize those circuits. Yeah. So that's all from my side. So if you have any circuit, yeah, for optimization of analog circuits, there is a one question. For optimization of analog circuits, GMID methodology can also be considered. Yes, yes. So we can also consider GMID methodology. Okay, so that one we can consider as a equation based, basically. Yeah. So any queries from anyone?
First of all, thank you, sir, for a nice session on optimization techniques, and also for showing few EDA tools for our participants. And can you please give me any research directions, sir, as some of them are very junior faculty, that is around 5 years or less than 5 years of experience. Some research directions in this area.
Research directions right now, actually, most of the designs we are having a simple circuits like operational amplifiers, so OTS and LDOs. Only simple circuits are there. So if you want to go for a specific up to now, this is only the CMOS technologies. Okay, so
Right.
there is no FinFET technologies or tunneling FETs, so it's not there. So, but for that we need a library. We need a libraries. Okay, so if you have that information, I mean, initially we need a data set. For the data set, if you like model the tunneling FET or FinFET with those, so we can implement that one also. That is one thing.
Okay,
And
sir.
second thing is like there is some in MATLAB we have some add-ons related to this farm optimization and particles farm optimization. So there you can go for that mixed mode design. You can consider the circuit directly, and you can do that. So that one is also fine. Yeah. So right now, maybe I can expect some question like, yeah, this is circuit simulation is fine. What about the layout? So when it comes to the layout, the problem is like if you have a different dimensions of the transistors. So generally what we have is like a pull up and pull down network. I mean, PMOS, we are having one dimension and pull down is another dimensions. Like NMOS is having uniform dimensions and PMOS are all having same dimensions for the most of the circuits. But here it is, there is a slight change, like only 0.1, 0.2 dimensions will be changed. So while we are going for the layout, so there you can go for the like dummies we can use and we can go for it.
Sir, I had one question, sir.
Yes, sir.
Sir, while for an optimization of an analog circuit, I've just considered your example and op-amp also.
Yeah.
Doing with your circuit simulator, suppose it would be an H-spice. Sir, how
Yeah.
we can correlate with this channel width with the output resistance?
Sorry?
What is the effect of the channel width on the output resistance? How can get I a
Channel-
perfect output resistance?
Channel
so
width,
that-
sir. Channel
Yes,
width.
yes. Channel width.
Channel width. So that channel width, we are writing a equation. Okay, we are writing the equation. So that was actually we are creating one data set.
No, sir. Actually, if I am just going the H-spice simulation for a two-stage and op-amp, I just want to reduce my output resistance. I'm getting some specific values. It would be in a kilo ohm. Suppose that I just want to reduce, or I just want to increase that. Then what? How can I take that particular channel width? It will be a hit and trial method.
Yeah, it's not hidden trial method. It's like we are having the different algorithms, optimization algorithms. So one is you are having the gradient algorithm. In gradient algorithm, we are going for a stepwise. Okay, so we are changing the W, like for one transistor, we are changing 0.1, 0.1, 0.1 like that. We are keeping all the other transistors are same. Okay, so we cannot done manually, right? So, and we can take the another transistor.
Sir, actually, it happens so now. It happens so if I just make this with the 35 transistors, I just make one op-amp circuit. It would be a very it would makes very difficult to get any specific value of W.
Yeah, so that's what actually, if you change the transistor size and you are looking for the simulation result, so then you need to verify it, right? So, but here what we will do is we are applying algorithm so that output verification result we are giving it as the input. Now we are checking that whether it is meeten or not. If it is meeten, if it is not meeten, the algorithm itself again take the another set of values. So that's what it is doing.
Sir, other than algorithm, if you just I go with a circuit simulation.
Yeah, circuit simulation, it is like if you are going for the n number of simulations, right?
Yeah.
N number of simulations. Okay, so that is the case. We are considering only changing something delta W change, but not the fraction of those values, right? So that is not going to be done at the simulation level.
Yes,
so maybe if you are considering the CMOS inverter, so there is a ZPU by ZPD ratio, right?
Yeah.
So yeah, if you are changing the dimensions, so the region of operations are going to be changing.
Absolutely, sir.
Right. Yeah, that's what it is. So here we are not bothered about only the single transistors. We are bothering about the n number of transistors. If you want to do this n number of transistors and combinations and all, so it's very difficult.
Okay, sir.
Yeah. Thank you. So any other?
Any other questions from participants?
Hello. Hello. Good afternoon, sir.
Yeah.
This is Mali, sir. So you want to know advanced computing techniques, benefits of ML.
Sorry, your voice is not clear.
Sir, is it audible right now?
Yeah, yes, sir, please.
How we can apply the ML based techniques to the approximate address and
If you don't mind, can you ask the question in chat box so that it's not clear your voice?
Okay, sir. Please post your question in the chat box. Okay, meanwhile, any other questions from any other participants? Okay, sir. Question has been posted in the chat box.
For approximate adder, no, for approximate adder, it is like it is a digital block, right? We are talking about the only analog circuits right now. Yeah, so it's a digital block. So where uh, maybe if you are looking for those digital blocks, maybe you can go for some digital control circuits using the algorithms. That is a again different story. Yeah.
Is it okay, sir?
Yeah, he said okay.
Okay, any other questions? Or if no questions, then shall we wind up this session? Okay, it's already 3:30. The next session resource person has also joined us. Thank you, Linendra sir, for your time and for a nice presentation or two. And you have also given 2-3 research directions for younger faculty. Chandran Tumati sir, do you have any question? Maharaj, please mute your mic, please. Okay, Arpita ma'am,
Sir,
please conclude this session.
thank you, Linendra sir. Thank you so much for sharing your valuable expertise with us. We wish to have you again in your future programs also, sir.
Sure.
Thank you, sir.
Thank you, Rao garu, and thank you, Ashrita ma'am. So thanks for giving this wonderful opportunity to share my knowledge on this stage. Thank you very
Thank you,
much.
thank you, sir. Thank
Thank
you.
you, sir.
Thank you very
Thank you.
much. Madam, please share the slide for the next session.
Okay, sir.
Already Shankar sir has joined us. Shankar sir, I have made you as presenter. You can check for the screen share option now. After a brief introduction, you can share your screen and go ahead with the session, sir.
Sure, sir. Yeah.
Okay, okay. Okay, ma'am.
Good afternoon, Shankar sir. So we're excited to again have you again for this session. So before moving on to the session, I would like to introduce to the participants who have not joined yesterday, sir. Mr. A. Shankar Rao, sir, member of technical staff and lead engineer at Advanced Micro Devices with over 8 years of industry experience in VLSI design and verification. He holds a master degree in electronics from NIT Kurukshetra and specializes in design for testability with expertise in SCAN and ATPG, memory-based design, memory grouping and repair, and SOC debug across both pre-silicon and post-silicon validation. He has extensive experience with industry-leading EDA tools such as Cadence, Synopsys, and Siemens, and has contributed several patents and research publications in advanced DFT techniques. His current research focuses on novel DFT architectures, memory reliability, and efficient test strategies for next-generation SOCs, while outside he actively has various interests and he pursues in trekking, badminton, cricket, and volleyball. So we are honored to have you again for this session, sir. So kindly
thank you,
share
ma'am.
your
Thanks for
thank
your
you, sir.
introduction. Yeah.
Kindly share your
Uh,
presentation and hand out the session, sir.
Sure.
Okay, sir.
Srinivas sir, can let me know like is my slides are
Yeah, starting slide is visible.
okay, sir. Yeah, I think that should be fine.
Okay,
So
Arpita ma'am, please take a screenshot. Sir, maximize
yes.
your slides, sir.
okay,
Or you
sure.
can change the slides. We shall check.
Is that fine?
Yes, sir. Yes, sir. Fine.
Okay.
Yeah, slides are changing.
Yes, sir.
Okay.
Yes, sir.
Screenshot over, ma'am.
Yes, sir. Yes, sir.
Okay, okay.
Okay.
Sir,
So
you can continue, please. Shankar sir.
sure, sir. Meanwhile, like I will because that streaming quality might be less, I will turn off the video, but I will continue that.
Okay.
Okay. Okay. Hello everyone. Good afternoon. So I think yesterday, most of the guys we joined, and you might understand what exactly the need of DFT or what are the topics we have discussed. You might get an idea like how the complex SOCs are built. Okay, I think just right now one lesson is happened, right? So they are talking about something analog and digital. You might check with some other way of testing or something, right? I don't know what exactly the question, but whatever I'm going to teach is completely how can we make everything as a digital, and finally we can able to test in everything. Like it's not only specific macros analog or thing, everything we can make it as a digital and we can test it. So in this session, right, I think the introduction to myself is already done. I specifically no need to give again. So I briefly want to go through like in the second session, what are the DFT techniques we are using? So because yesterday till we got like why we need a DFT, but now what is the DFT and what kind of tests we are using to test each and every defect in our systems. And another one is how the advanced DFT techniques, how the advanced DFT techniques can used for testing a minute defect in the design. Okay, so let's quickly go through like the agenda of this today's presentation is I will give you a brief overview about like the basics of DFT and yesterday I given a very basic idea like how the scan flip flop, right? I will start with that again, and how different design rules, because in order to do efficient testing approach, we need to follow enormous DRC checks. DRC is a design rules check. Okay. So, guys, please mute yourself because we should not get any disturbance, because it should be something interesting. Okay. And another one is the traditional DFT models and advanced DFT fault models we will discuss, and how to increase the yield. Okay. Yesterday, I was very clearly told how the industry revenue or like any company growth is completely depends on how the yield percentage and how exactly the defect quality they are testing, and how exactly the chips they are manufacturing and they are producing and selling it to the customers, what was the guarantee like it is a defect free. How like I told you like what is the DBPM effect, right? This is defective parts per million. So how can we reduce, not only reduce, how to achieve a zero DPPM? Okay, so means whatever the chips we are manufacturing, at any cost it should never affect any of the customers or any of the application fields. So that means we should get a zero defective chips out of the fab. Okay, so to achieve that, what kind of techniques we need to use? Okay, so you should always think in that way, like in the recent industries, what kind of techniques they are moving. Okay, so traditional things everyone is following, but what were the advanced one? So because we need to always upgrade our skills, right, with respect to the recent industry trends. So what kind of techniques they are using and all we will learn. And in between, I will give you some very high level insights like how exactly any SOC or any integrated circuits will looks, what kind of components will be there, and how the internal logic will be there. So these things you will get a good experience if keep understanding. Okay, and I'm expecting each and everyone at least should ask one question. If I didn't get any question from one, I will only ask each and every person from my session what is you understanding from that. Okay, so please keep that in mind. Let's quickly go through. So this is, I was just included the same one. To first start any DFT technique, we should know about the simple D flip-flop. Okay, so everyone aware of normal D flip-flop, how it will looks like. But when we want to do for a DFT testing, so we should make it as a scannable. Means we will add an extra circuitry to make it a user-friendly testing circuit. Okay, so that's what you can see the scan D flip-flop is having one mux, and it has a two extra ports, that is SI, that is a scan in, or we will say a test in, and another one is the mux select line, so that is scan enable or test enable. So if you see here that this D is same as the normal D flip flop, it will be as a functional path, and whatever you are going to test or whatever you're going to apply any vectors to that system, so you will use this test path. So here the test path is your test input or test enable. So until and unless you are enabling this signal, you will be still a functional. That means whatever the your designer is intended to do. So in previous session I told the DFT is an extra circuitry we are inserting in the design to make sure each and every part of your chip is tested, and you are giving a concern like there is no defect in my design, because as we already know, the functional approach is very long runtime approaches. So in order to go with the shorter runtime, saving the test cost, you should go with the advanced DFT techniques. So keep in two things in mind. We should always effective patterns we need to generate, and we need to reduce the test time. Always, if you reduce the test time, your test cost will reduce, because this SOC or any integrated circuit testing is per second calculations. Okay, it will be not per day or per hour or something like that. So every second will be at millions of dollars cost. So that's why if you reduce the test time, you will save the test cost. So our target towards effective DFT techniques to cover most of the defects, and it will reduce the test time. So here you should understand the basic few things. This is the previous slide only. So here, whenever your scan enable or test enable is high, you are going to apply your test inputs. Whenever your scan enable is going low, that means you are observing or whatever the intention of the functional logic from the deep path. So whenever your scan enable is going zero, you will take the response from the your actual functional logic. Whenever again your scan enable or test enable going high, you will unload or you will just shift out the your expected response. So this is the basic understanding about how the scan will work. Now I will give you one example how we will stitch scan chains in our design. So before that, you can understand whenever we are going to do a scan insertion or any ATPG techniques or any DFT related techniques, first we will reuse the D flip flops, whatever the flip flops, into a scan flip flops. So you can see this is the scan flip flop, right? So next time I will represent any scan flip flop will be like a normal D flip flop. It has extra two inputs, a scan in and a scan enable. So this you can keep in mind. So let's say how the scan stitching will happen. So, guys, you can understand the complete DFT if you want to understand the basics. See this one diagram I can give you, like you will almost get 70 to 80% of how exactly the DFT testing will happen. So, as I told previously, the functional testing will basically we will use the inputs, okay, the primary inputs, and we will give a lot of logic and this complete huge combo logic. It might be millions of gates or billions of gates, so much of combo logic. You need to give a input and you can get the response, and after that you can give it to next one, and maybe this combo logic has some dependency on this, something like that. So you want to test this kind of combo logics or complete design. I just given one example, two combo logics, but it should be applicable for hundreds of such combo logics. So first what we will do, we will use this existing flip flops. Okay, if you can ask if there is no flip flop means even we can add extra flip flops also. First we will make these flip flops to scan flip flops. How I will make? I will add extra two ports, that is one scan in and a scan enable. Okay, the moment if you add this muxing logic, okay, by adding this scan in and scan in port, you can stitch these flip flops into a single chain or multiple chains. How you will stitch? You can connect the first flip-flop, okay, on the flip-flop Q to this SI and another flip-flop Q to the SI. Now you can see the scan chain, how it will stitch SI to Q, Q to SI, SI to Q, Q to SI. So just imagine this. If you want to get any input for this flip-flop 2 or flip-flop 3, when you don't have this scan chain stitching, how you will get? You will give a input D and you will pass that inputs through a huge combo logic. Okay, and after that you will get the output from that and you will again feed to this one. Now what will happen if you want get a particular value, you want to test this combo logic and you want to any value at this Q or any value at this Q. Okay, let's take this one, second flip-flop output. It's very easy. You can just use two cycles, okay, two clock cycles, and you just enable this scan enable and give two clock cycles. Whatever the input you are giving through SI, it will come, okay, here, whatever you want. So you don't have any dependency on this. But as you understand what is this combo logic, you know what kind of inputs we want to give and to test, right? Anyway, we will discuss in detail what is there inside this combo logic and how we will test. But you can understand the basic idea of scan is just we are getting the controlling of these nodes. And similarly, even we can observe these nodes by putting our scan logic. So this is the basic idea of a scan chain, how it will be going to test a huge combo logics in our design. So this is one way of testing the, like instead of going for a functional or conventional testing, we are going for the DFT related techniques. So this is the scan enable. Whatever the scan enable here we are giving, it's a global scan enable. Like you can understand, the complete scan chain will run with a single enable. So the moment if you are enabling the test mode, when you are keeping your design in the test mode, means you are putting the scan enable is one, means you always have a controllability, means whatever the inputs you want to apply, you will apply through this SI. Okay. And the moment you are giving the required inputs for this combo logic to test whatever the logic which is inside that. So after that, you will make the scan enable to 0. Then what will happen? It will take the whatever the inputs you are applied at this combo logic input and the output which you are getting, you are capturing through this D path. That is a functional path. So after you got the functional path, this D to Q, then what you will do? You will again apply your scan enable is high. That's why again you can get the response whatever you got from this output that you will shift out. That's why guys, I think you can see here I told the shift and unload, load and unload. Okay, this is the shift and capture. So you are applying the inputs and you are getting the response capturing from the D path and again you are unloading that one. So you are just giving the patterns whatever you want. And after that, you are checking the complete combo logic, what output it is giving. And you know what is the expected output also, that you are comparing with the unloading. And you will make sure like, okay, my design is pass or fail based on that. So it's a basic idea of how the scan chains will be stitched. Okay. So last time in the previous session, someone asked like how exactly your complete scannability will depends. So this is the main two interesting key points when any DFT engineers want to design or test anything, they need to consider in mind like the two pillars of the DFT is controllability and observability. You know what exactly the controllability and observability? So the name itself, you can understand what exactly the controllability means. In any design, in your functional logic, we might not have any access to inside your circuit or inside your design. Only the circuit output signals or input signals only you have access. Because of that, you will get a huge runtime or testing time. So for DFT, we can get a controllability or we can observe any node within our design. Okay. So what is the controllability here? It's a measuring of every node. Okay, whatever the node of a particular design within internally, whether we can apply whatever the required inputs we want to apply. Okay, not the system wants to apply or whatever the logic it is getting. Whatever the inputs, if you want to apply at a particular node, if you are able to apply means you have the controllability of that node. Similarly, observability means we should not wait the output signal to reach at your chip boundary. We should not wait until there, but you should have the feasibility to observe any node, okay, at what is the response of that particular node. So that is called observability. So if you have a design and in that you have some 10 nodes, and in the 10 nodes you have a all nodes controllable and observable, means you are achieving 100% of coverage. Okay, so the goal of the DFT engineer or the goal of the DFT engineer or the expert is convert all the non-controllable, non-observable nodes to a controllable and observable nodes. Okay, so before going to different techniques, I just want to give like we are seeing a lot of manufacturing defects. Previous session we understand, right, like how different kind of defects like breach are open or something like the electrostatic diffusion or like some of the like opens and all, right. So those we can make the defects into a different fault models. So there are few fault models from beginning of the like VLSI industry they are following. Those are like a traditional DFT fault models, that is a stuck-at fault model and a transition fault models. You might aware like this stuck-at means it's a DC faults, or transition faults mean AC faults they will call. So stuck-at faults is basically two types. That is stuck 0 and stuck 1, and the transition faults also we will call it as actually delay faults. This is quite interesting. We cannot say it's a traditional one. This transition faults will be transformed into so many other ways to make it a very advanced DFT techniques. So first the DC fault models we will go a little deeper. Exactly this stuck means you know, right, stuck basically it is stuck to some particular value. It's not changing the value whenever we want. Okay, so in such scenarios, you can see like one example I have given, the first input node, one of the input node of the AND gate is stuck to 1. Basically, what is stuck to 1 means in a real picture is it might be connected to a VDD, okay, is this power source, or it is connected to a node where it is connecting to VDD, it might be, right? And another one is you can see this output is stuck at 1. So there is different ways, okay, we can get this stuck at 1. This is just a model, okay, fault model. In real case, it might be a bridging fault, or it might be a directly stuck to the VDD. So many scenarios we will translate into a stuck models. Similarly, I think stuck at 0. What is stuck at 0? Even we want to apply some particular voltage, that particular node is not able to get that voltage. Okay, so because it might be connected to a ground and you are unable to break through that node. So this kind of faults will be a stuck at 0 faults. So you can understand basically one AND gate you can take, and how many maximum faults can happen for a 2 input AND gate. You know, right, like it might be a stuck at 1 or it might be a stuck at 0. So for one node, it is 2 faults, means this 2 input AND gate has 3 nodes. So that means 3 nodes into 2 means it will be a 6 total stuck at 1 and 0 faults will happen. So now you can find out your complete fault count in your design based on this approach. Okay, stuck at 0, stuck at 1. Let's say you have 10 AND gates like that, means you might have 10 into 6, 60 faults. So that means the number of faults will be huge when you have a billions of trillions of transistors or gates in your design. Okay, so I will just give just an idea, because I will not go any theoretical or mathematical calculations, because this program itself to enrich and make your thought process something beyond the existing techniques, right? Because you can get it in a books or somewhere in some other tutorials also. If I explain this, keep this basic stackets and all, but how can we leverage, or how can we make it effective way of testing? Okay, so everyone can test the 6 faults, but how are you making sure you can reduce the 6 faults to something less? How it is possible? That way we can think, right? So okay, so just let me take a pen. Just you can see here the stuck at 0 is there. Let's say if you want to detect this stuck at 0 fault in your design, basically what you will do, when it is stuck at 0, always the approach is we want to get a output of 1 year, because it is stuck to 0 means it is a grounded, but we want to expect a high voltage at this, means if you get a high voltage, then you are make sure there is no fault. But if you are not getting a high voltage here or 1 here, then you can understand this node is connected to ground. How we get, you can, right, and get the truth table. So what inputs if you apply, you will get a value of 1 here. So that means you cannot apply 0 0 or 0 1 or 1 0, but you can apply that last set 1 1, and you are make sure when you are applying a 1 1, you should get a value of 1. But when your system or when your design is stuck to 0, you will get a response of 0, and you can understand that tool. Make sure when you are applying a vector of 1 1, you are not getting the 1, it is getting a 0, means you have a fault, you have a defect at your AND gate output. So that is detected by the vector of 1 1. So it's just an idea like how it is happening. Okay, like that, let's say if your output is stuck to 1, okay, high voltage, but you want a logic of 0 here. So when it's stuck to 1, right, how can we find out? We want to expect a 0 here. Then only you can make sure my node, whatever the node is, not connected to a VDD or source. So when you want to expect a 0, you have a 3 possible combinations of vectors. So you can use either 0 0 or 0 1 or 1 0, right? So now you can understand in a functional wise what we can do in order to test this AND gate. In a functional ways, what we will do, we will apply all inputs, okay, 0 0 0 1 1 0 1 1, okay. But in a structural way, you want to understand whether this AND gate is working fine or not. Guys, I'm just explaining a very basic 2 input AND gate. Just imagine there is a millions and billions of gates is there, how effectively we can use the same principle when you are applying different vectors. So in a functional case, it will use this complete 4 vectors to test your AND gate is working fine or not. But as a DFT engineer or a DFT expert, I don't want to use all this. I can use only a 2 vectors. I can make test all my faults in my AND gate. Like here 2 faults, stuck at 0, stuck at 1. Here 2 faults, stuck at 0, stuck 1. Here 2 faults, stuck at 0, stuck 1. How? I will going to tell that one. So first, okay, here you can say if you want to get a 0 output, you can apply any of the combinations of 0 0 or 0 1 or 1 0. Correct? So when as a DFT, I will use out of these 3, any one I will use, and I will make sure my output is getting tested stuck at 1. Okay. So this is where, like, let's see this out of these 3, we can use any one vector to make sure your AND gate is tested all the vectors. So let's say this is the one simple example. When you want to detect a stuck at 0 fault of your AND gate output, what is the input you want to apply? I want to get a output of 1 here. So in order to get a 1 here means you need to apply 1 and 1. Here there is a magic, guys, you can understand. The moment when you are applying 1 1, indirectly you are already checking this node is not stuck at 0. Okay, that means this node is, if it is stuck at 0, when you are applying 1, you will not get a value of 1 here. Similarly, when you are applying a 1 here, if this node is stuck, okay, if this node is stuck to 0, then you will not get a value of 1 here. So the moment you are going to test stuck at 0 fault of a output, you are indirectly testing, okay, the stuck at 0 of your input nodes, both input nodes. That means the one vector which you are using for this one, you are able to detect almost a 3 faults. Got it right? So you no need to see, that's what the DFT approaches will identify which one is the best and optimal approach to get a less number of vectors. See, let's say here 4 is there. If you want to apply 4, you have taken some 2 minutes, means when you are applying 2 vectors, it will be 1 minute. That means you are almost 50% you are reducing the test time. Imagine if one AND gate is this much you are reducing, means in a millions and billions of gates, it will be a huge, right? So similarly, you can see this is a stuck at 1. When you want to test a stuck at 1 fault, you need to get an output of 0 here. You want to expect 0. So when you want to expect 0, you have a 3 possible combinations. You can use any one. Okay. But when you want to any one means you can make sure that time it should be able to capable of doing a stuck at one testing of this one. So I prefer you can use a 0 1 or 1 0. Okay. So these combinations is best effective one than the 0 0. Why I will tell 0 0 is the moment if you put 0, AND gate is always sensitive to 0. So you will get output 0. Other input, whether you are applying a 0 or 1, you are not able to understand, right? So that's why you can use the sensitive one, which is AND gate, should not be, you should not apply 0. You should apply 1 like that. So this will give an idea about like how a stuck faults can be detected at various stages of the combinations. Okay. So similarly, we have a transition delay faults. Okay. So what is exactly transition delay faults? Basically, delay faults is nothing but same as a stuck faults, but here you are doing the fault analysis with the timing analysis. Okay, timing based. So basically, what exactly I can say is, let's say you are expecting a 1 to 0 transition or 0 to 1 transition. Okay, so that 1 to 0 transition should not take the time whatever 1 to 0 transition is happening. It should not take more time whatever your clock period or whatever the time you are giving it the certainty time. It should not go the beyond that. Okay, so let's say nowadays the testers or chips or the functionality of the frequency is a megahertz gigahertz, right? So if that much high speed applications we are using, then you can understand your signal whatever it's going to 0 to 1 or 1 to 0, it should not take as much as time within your limit. So let's say here, what is a slow to rise fault? Okay, slow to rise means you can understand. I think this is the slow to rise fault. What is this slow to rise fault? In the slow to rise fault means whenever you are like you can see this OR gate, so you are giving a 0 and 0 to 1 transition. Basically, what you are applying here, and OR gate, and you are giving one leg is 0 means other leg whatever the input it will reflect, right? So we are expecting a 0 to 1 transition same as whatever input you are giving. Agree? But due to some defect or due to some issue, many lot of things might be happen inside this OR gate. You are getting a output after some time, so there is a delay. Okay, there is a huge delay of your output response. Whenever you are expecting the value at this time frame, you are not getting, you are getting a 0. That means the value you are giving a 0 1, output should come as a 0 or 1, but you are getting again still 0 within that time. So this is a slow to rise fault. Okay, similarly, what is slow to fall? When you are triggering, like when you are the signal is falling from 1 to 0, it's taking a delay. You can understand this is the 1 and this is the 1 to 0 transition. So one leg of the input and gate is 1 means always you are getting the transparent of this another input. So you are expecting a clear signal like 1 to 0 transition. It's a good response, right? But due to some defect or some issue within your AND gate, okay. So due to that, you are getting your response still 1, okay, after some time. So this is, we will say like slow to fall. Okay. So, guys, actually, it's a major concern. This transition faults is the major concern because when you are running a gigahertz, 2, 3, 4, or 5 gigahertz of frequencies, this very minimal time the response should happen means this might be a more error prone. Because of this, a more number of defects might happen. Even in the silicon, you might miss some of the faults testing, and this might cause a failures in the automotive systems or a failures in your medical systems, or it's a failures in your any of your mobile or any of your laptop gadget. Anything might happen, right? So that's the reason we need to very carefully design our techniques to catch this kind of delay faults as well. Okay, so before going to tell like how exactly this delay faults will be measured or calculated and all, I will give you some golden rules. Whenever you want to test any logic or any design, we need to follow some of the ATPG or scan design rules. So those rules will be a, you can say like it's a standard rules or thumb rules. If you follow these rules, the 80 to 90 percentage of your testability structure is a very effective. I can say like uh, with the use of the scan design rules, you might not get 100% coverage, but your scannable design might be testing up to 90 or 80% of your faults. So what was that one? You need to make sure your design, whenever the design is creating, you are a design engineer, you should understand how should I do a effective design. Like all the clocks, whatever the internal clocks, should not be coming from the somewhere derived. Okay, some of the output is controlling another clock, means it's not a correct one. So you should use always a top level port to propagate your clock. Similarly, loop back circuits will be there. So functional wise, I will not say anything wrong with respect to these things. You will get a loop back circuits, you will have a clock which is derived from the some other laws, but I'm talking about the test wise or a DFT wise. So when I'm a DFT engineer, I want to make sure my circuitry is everything proper controllable, because I need to get a controllability and observability from each and every node. I'm keeping that in mind. I'm applying these design rules to make sure my circuitry is proper to test the design. So like we should not use the gated clocks. It must be controllable, and latches should be very transparent, and buffers and everything should be transparent. It should not be dependent on any other cases. And clock should not be used as a data path, because clock, if you are using a data path, clock will use, when you are using a high gigahertz or megahertz high frequency, your data will be toggling that much speed, means your power dissipation will happen and your circuit will might burn. Okay, and you should bypass the memories in scan mode. This is very important point. We'll discuss a little bit later time, but your memories will not be tested in your scan, but how your memories will be tested separately. And it should be like some of the things we are putting a scan chain, right? So the negative edge flip flop should be always followed by a positive edge. This is a very big topic we can explore. Okay, why in a scan chain a negative edge flip flop should not be followed by, okay, basically it should be followed by a positive edge. But what is the problem if you positive edge followed by a negative edge? Your data might be lost, because of that positive edge will, after that immediately negative edge will come. So whatever you are expecting the data in the next flip flop, it might lost. So this is some basic rules. Like for example, I will not go with the very detail, but you can understand like what kind of design checks we are doing. Okay, so this we can apply at any stages of the logic. This is the one, before scan insertion or before a DFT engineer entering to the picture, your logic will be like this. Okay, one of the flop output is giving to clock. So that means you are completely depending this flop to do any action. You must configure this flop, and that output should go and drive this clock. And are you sure this output is giving a clock pulse, or it might give a random pulse or random values also? It might not be a actual clock structure. This might looks like a this also somewhere some other signal also, right? So we don't know. We cannot predict that. So in that case, how can we make sure it should be a properly controllable? So that's where the DFT logic we will insert. Okay, so you can understand here the same structure, the same design how we are did in a scan chain, right? Here you can understand the queue path we are adding a one mux, that's all. Okay, the mux select line is your test mode. See, it's very simple. So whenever you are your test mode is 0, that means you are in a functional mode. Functional mode is nothing but the chip actually, however it is going to work. It's not related to any of your DFT or test wise. So that means whenever it is 0, it's your output, whatever the output is getting, and it's going to the clock. So absolutely fine, because you are the designer. For example, you want your clock from this one, but I'm a test engineer. I don't want my clock from this. So that time what I will do, when I put the test mode is 1, means it's in a test mode, a DFT mode, I will control the clock from the top clock. So I can give whatever the clock here I want to, okay, to do whatever operations which is performed with this logic. So that can be achieved by using my top clock, and I can directly drive this clock. I don't have any dependency on this. So this is way how we can make the design is more DFT friendly. Okay. So one more thing is, see, we have a flops and there is a lot of synchronous, asynchronous set and reset signals. It is a similar way you can see this reset signal. Okay, this is synchronous low signal, reset signal is coming and driving from another flop. It's not exactly this flop. It might be controlling from some AND gate also, you can think. Not only this flop, just think in such a way that, so this some other logic is controlling, means it's not a DFT friendly or test friendly. So what we will do, we should have a control. Always we should get a controllable, because here you don't have a controllability or you don't have a observability. You can keep these 2 points. So when you don't have a controllability of this reset of this flop, it's difficult to test the logic which is connected to this output of the logic. Okay, so what you want to do, I will insert a OR gate, and you can just see OR gate on input. I'm giving the same as the functional case, but I'm adding a test mode signal, my control signal here. Whenever I want to do a reset, or when I want to do a set, or whenever I want to do anything with respect to this signal, I can directly give it from my test mode. Whenever test mode is 1, it will drive as a 1, and I can do my perfect operations here. Okay, so I was completely removing the dependency from somewhere functionally it is connected. I'm directly giving a controllability of my signals, whatever the test signals or clock which I have, from there I can control the logic. That's where I'm getting the controllability and observability from the designs. So another example, you can see this is a clock. Previously we talked about reset. This is a clock. This you can see. You know what is this? This is a okay, derived clock. Okay, so it might be when you are getting a clock. This is a when you are giving a negative means it might be a divider 2 clock. So you are getting these flip flops. The clock is off of the clock, but let's say this is a functionally you want to make sure. Okay, this is 1 GHz. Okay, this clock is 1 GHz, means here you will get a 500 MHz, and you are giving these flops to a 500 MHz input. That is fine. Functionality absolutely fine. When I'm going to test a DFT engineer, I don't want to be like what is the internal things is happening. I want to make sure my clock should come due to whenever I'm playing my test mode. So it's simple. I have added an extra logic. That logic might make sure your design will be a controllable and observable. So here also the test mode is 1, then only I will get my clock and it will go and distribute to these clocks. But whenever this test mode is 0, you are keeping the chip as it is, the design as it is, as a functionally how the functional working principles. Okay, so this clock only will go and test. This is the way we can make sure in our design, wherever the controllability and observability is missing, there we can make that circuitry proper way to it's a testable, test friendly. Okay, um so previously we discussed a different number of vectors, and we are applying more number of vectors to test a small gate also. So now the concern is how the test cost and test vector time we can reduce, right? So there are different approaches is there. So I will give you a basic approaches. So right, there are 2 approaches when you are following with the fault approaches, like that is fault equivalence and fault dominance. I think I already given an idea about like what is the equivalence, but I will go as what exactly the fault equivalence and fault dominance. These are the 2 best techniques we can make sure our DFT vectors or patterns can be as minimal as possible, and it should cover all the faults. Okay, so I just given one example. You can see here what exactly the fault equivalence. Basically, let's say there is a fault, 2 faults are there. If those 2 faults can be detected, okay, by a same vectors, we can say like it will be a equivalence faults. Okay, so the 2 faults F1 and F2 are equivalent if all tests that detect the F1 and also it will detect the F2. Okay, similarly, what is fault collapsing? That means you can understand if the same vector is able to detect 2 faults, means we can make the fault collapsing. Means we can already remove one of the vector from that, and we can make sure okay, one vector is sufficient. Or out of these 2 faults, we are able to okay, one fault if it is tested means obviously other fault also will get tested. So this is the rule. Actually, what is the equivalence rule? Let's say I told you if you want to test a stuck at 0 of the output of AND gate, it is indirectly you are already testing a stuck at 0 of input and another stuck at 0 of the another input. So that means you understand here the 3 faults. Okay, previously this AND gate is how many faults will be there? Total 6 faults. Okay, 1, 2, 3, 4, 5, 6. But by using this fault equivalence and fault collapsing approach, what you can do, the moment if you're testing stuck at 0, you're able to test stuck at 0 of input 0 and input, right? Both inputs. Then you can reduce the 2 faults. You can remove, just keep 1 fault. That means what is the total number of faults now? Reduced from 6 to 4, correct? So like that, the number of faults will be reduced. But indirectly, you are saying those faults will be tested internally, okay, because of the effect of another fault. Similarly, OR gate. Let's say if you are stuck at one of this OR gate is also covers the stuck at one of other inputs. Similarly, it's not gate, you know, right? One it means 0, 0 means 1, like that. Even when you know the AND gate and OR gate, you obviously understand what is the NAND gate. So the stuck at one of your NAND gate, you will able to test the stuck at zeros of your inputs. Similarly, a NOR gate. This is the way it goes. So this is one way of we can reduce the number of faults. Okay. And this is the fault equivalence example. I just taken one combo logic just for your understanding. You can see we have 1, 2, 3, 4, 5, 6, 7. Okay, total 7 gates we have. So these are all two input gates, right? So you can see how many total, like almost 15 faults will be there. So in this, when you are applying the fault equivalence, that means when you want to test this stuck at 0, it is always covering, right? So when you remove this orange or the red color faults, you can get a fault equivalence. After that, the collapsed ratio is just 16, okay, out of 30. So that means you are getting a 0.53 collapsing ratio. That means you are making your faults as consolidated as, because the number of faults, how much you are able to consolidate, you might reduce those many vectors, because one vector can cover multiple faults. That is the only motto behind. Okay, another example you can take. Okay, see, this is same. It's another combo logic, but you can understand when there is a net. You can understand when we are. You can this is the point. You can ask me a question like, this is the same output is going as the input. Sir, why are we going to do a fault analysis and get output as well as this OR gate input? Okay, this is very, very important. Then you can understand the wire, okay, the net might be a same or it might not be the same. So if it is not the same, as a DFT engineer, if I able to test until here, okay, making sure like, okay, I'm very clear, I don't have any fault, you might get a fault at this net also. Okay, so I should not lenience, or I should not over committed. Okay, I was able to test this net, so it will anyway going as giving to as inputs for this one. I will not dependent like that. I will specifically take this output, okay, this OR gate, and what is the inputs which is coming, okay, from this. Even though this output is driving, still I will go and test at the input of OR gate also. So that means I will cover each and every node, every net, every wire, every logic to be a defect free. So with that confidence only, I will go, my chip is 100% is tested. Okay, doesn't have any defect in my design, like that. So here the collapse ratio is 20. So how much our more faults we are doing a collapse, that will be a the great thing. Like you can say like your reduction of patterns or test cost is that much great. Um, Another technique is a fault dominance. Okay, it's almost similar behavior of the fault collapsing and equivalence, but this dominant faults is understanding and identifying the dominance fault is very, very important. Why means, previously we talked, okay, if two faults tested by the same vector means we will remove one fault because anyway it will indirectly detected. But you can understand which fault is the dominant one. Dominant one means because of that, the another fault is already getting detected, but it can detect even furthermore other faults also. If that is the one, see, if all the tests of, for example, F1 detects another fault of F2, then F2 is said to be a dominant of F1. So I will give you one example what exactly this dominant fault is. Let's say this F2 is stuck at output, F1 is stuck at input. So to test F2 stuck at 1 here, okay, that means we need to apply a 0 here. You might get so many things. Like what was that? So many inputs we can apply. So 0 means you can give a 3 inputs means almost all other vectors 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0. Any input is 1, you can give those many vectors. But you can see this second one is this stuck at fault one. So in order to test this, you must need to apply a 0 here. And in order to propagate this 0, okay, you must need to apply 1, 1 here, because we know only this is a stuck at 1. So that's why I'm giving a value of 0. Then if you want to propagate this 0, because I want to get a 0, then I obviously should give 1 here. You can ask, sir, I can give 0. Then you don't know because this 0 is going or this 0 is going. That's why this F2, this F1 is only a one vector. Okay, 0, 1, 1, 1. Okay, so that means how you can exactly say, okay, here the fault F2 dominates the F1. That means the F2 is removed from this fault list. So this we can remove because this fault is able to detect even in the F2 also. Okay. And you can see the dominance collapse defaults means after that, I told you, right, each node will have a stuck at 1, stuck at 0, stuck at 1, stuck at 0. Then this 3 input and gate will have total 4 into 2, 8. In 8, this 4 false testing is sufficient to make sure your AND gate is perfectly working. Okay, let's assume it's a 100 input AND gate or okay 125 or 128 input AND gate. You can understand the combinations, how many it will be. In that, you no need to apply each and every vector. Just a 3 input, you have a 2 power 3, 8 vectors. So in a functional case, if you apply 8 vectors, in a DF device, you don't need to apply 8. You can take some 4 or 3 in 2. However, it is possible. You apply this fault dominance and fault collapsing, fault equivalence, these two principles, and you make sure you are able to reduce your number of test vectors, making sure you are able to detect all the faults, not compromising or not leaving any of the fault. This is another example. Okay, this is a dominance faults, right? Previously, we only discussed about the fault equivalence and collapsing. Now, with the help of this dominance, even further we can reduce the number of faults. How? The same example I have taken here. Previously, we got around something like 0.555. But after this dominance, this even like the stuck at 1 at this output is dominated by these two stuck at inputs, right? So even we can further 16 to 15 y we got. Okay. So another example, this is also previously we got something around 16 something. Now we got 18. So that means some extra faults can be eliminated by using this dominance. Okay, fault dominance example. So this is where this is the basic principles. There are so many advanced principles are there, but I want to give an idea like how can we think about each and every node is getting detected and tested with the minimal set of vectors. Okay, so now you know like this each gate is a standard cell, correct? So one more things I will get. Whatever this conventional DFT techniques we are using, right? Are you think these are the sufficient or to test all the faults like in a billion numbers of transistor logic in our design, right? Is it really sufficient to test all the faults? Okay, I don't think so. But I will show you some 2, 3 or some 4 minutes simple video to make sure like whatever till now we discussed. After that, I will ask one question: is it really sufficient whatever the techniques we are following or not? Okay. So I just want to give an idea like how a complex SOC really looks. Okay. Guys, please understand from this. You might get a lot of understandings how really the chips will be manufactured, how the internal architecture, the internal design. In a SOC means we will talk simply like what is an SOC? It's a system on chip, it's an integrated circuit. What kind of logic there inside? Inside each IP, each macro, each core, what kind of transistors will be there? Like for example, how many multipliers, how many adder subtractors, ALUs will be there. So each one consisting of how many transistors, how it will perform. You will get an idea. So just please carefully listen, and you can just we'll talk after that. Okay. So I think I just want to give a touch of like how exactly the architecture or the designs, how internally any integrated circuits will be built. Okay. So till now we are talking about AND gate, OR gate, how the standard cells will be tested. Okay. So is it sufficient, whatever the techniques we discussed, to make sure the microscopic fault also can be detected, or whatever the faults even might be escaped and it is giving a huge impact in the system, right? Whatever yesterday we talked. Okay. Can we able to detect those faults also by using this traditional DFT techniques? Okay, I don't think so. I don't think so. These DFT techniques or whatever the conventional DFT techniques till now we discussed, it's a basic principles. How can we test? But if you go with that, we might be a chance escaping some of the defects, and it will impact in our day-to-day life applications. Okay, so I just want to tell these are the conventional ATPG techniques, right? The stacked faults and transition faults. And if you follow with this, and are we really able to achieve the 0 DPPM goals with the following this traditional ATPG stacked faults or transition faults? I don't think so, right? So we need to go beyond this. What was that? So our idea is always to achieve how our testability can increase. How can we able to detect each and every fault? Every time I'm saying each and every fault means we should not neglect any small fault. It might escape and it might cause a huge impact in the system. So such a way that we can find out one testing approach is called a cell-aware test. What exactly the cell-aware test? So till now, I will show you like the cell-aware test is nothing but like see traditional ATPG. What we are doing, we are going and taking each and every gate and we are checking just what kind of faults it will be happening. Okay, each and in every input nodes and output nodes of the design. But when we are moving to towards a lower technology nodes, see basically until 2005, 7, 8, 10, that time we are going to 64 nanometer or 128 nanometer technology nodes. And these technology nodes might not be that much error prone because the standard cells are very tightly manufactured and created. Okay. But now we are not hesitating to go and do inside of the transistor also, like inside of the your AND gate. So you can see like, let's say like a two input OR gate. If you go internal structure of this OR gate, how exactly the internal structure will be there? You might get a fault at in between A to B, or your VDD is connected to one of the input, or might be like source is connected to the drain. There might be a lot of chances because you are going to a lower technology nodes. You are using a 2 nanometer, 3 nanometer, 5 nanometer designs. So the moment if you are using a high complex high complex designs and lower technology nodes, there might be a lot of chances of errors. So the testing of faults at inputs and outputs of the nodes might not be sufficient. You might need to go inside your standard cells, inside the design. It's at transistor level. Okay, there might be a capacitor. It might not working properly. Because of that, you might not get the expected output at your output A or expected output at output B. So there might be a lot of possibilities. Or you might have this VDD is connected to your A, or might be like your B is connected to your ground, or might be a drain and source will be a connected. Any kind of possibilities happen, right? So how can we test this? So that's why we are using the another advanced DFT technique is called cell aware test. So what exactly this cell aware test will do? It will go and do at the layout level, like internal to the standard cells, and there it will do all the possible combinations of uh, connectivity, bridging, error, and short, everything, every possible kind of testing it will analysis. But for that, what kind of inputs we need to give? We need to give a layout input. Okay, how the internal architecture, that OR gate or AND gate, how's the physical design level it will be there. Okay, basically this is physical aware faults also we can tell. So those faults also we can able to detect by using this cell aware test approach. So I will give you another example how the traditional versus cell aware ATPC. Okay, let's say you have a muxing logic. Okay, basically this is 1 2 3 3 input. Okay, 3 is to 1 mux. So it's designed by using a 2 input 1 mux. Okay, 2 is to 1 mux by using designing a 3 is to 1 mux. So when you are using a traditional one, you might detect a stuck at 0 fault at here. Absolutely fine. You are expecting corresponding output here only, that is obviously fine. But what if something within this internal mux logic might have a net A and net B, it has a bridging fault? How are we sure? Whatever the test vectors or whatever the things you are able to detect all the faults at this inputs and this inputs is sufficient to detect even the internal one? Not sure, right? So that's where you can think about how can we go even beyond the standard cells, and how can we predict, because we can't assume it might be a proper one due to the manufacturing case. It might happen, the bridging might happen, because yesterday we discussed what is the possibility get happen the bridging or short or any electrostatic diffusion, anything. There is a lot of chances during the manufacturing time we might get, right? So how can we detect? By using this cell aware test we can detect, right? So even I just given different defects or the models in the cell aware, like we can see like the port open defects. So this port to the internal to the node we can detect, and the bridging defect. So one node to another node, there might be a bridging. Okay. And the port bridging defect. So even it might happen from the VD to ground, the bridge might happen. And transistor on, always on might happen when you are connecting from source to drain. Okay, the T on and T off. So transistor level various faults will be. I just given you some 2-3 examples here, but there is a hell lot of possibility of defects in various nets, various nodes, various metal layers. So all these kind of faults can be detected, okay, by using this advanced DFT technique that is called SL aware test. So there is a flow is there, I can tell you, because I will not go any theoretical way. I don't have interest to tell about theoretical concept, because you might get a lot of things in any book or any materials. So basically in this cell aware test, what we will do, the main thing is whatever the standard cells will have, we will have this layout extraction, and with that layout extraction we will do a layout aware analysis by introducing all the parasitic elements. Okay, so that means in my transistor, what was the capacitance I'm using, what is the gate resistance, what is the drain source resistance, what is the everything, all the things I will keep it in a very practical. And what might be the getting a chance, I will do all this analysis, and I will do this analog fault simulation. In that I will identify which are all the like final fault model generations, and because of that I will just see the view. Cell aware view means what might be a chances of getting faults within the internal to the cell. Okay, so is exactly that layout extraction. So okay, this is also a kind of, you can see from this, right? This is basically my layout. Okay, this is the GDS2. So you might see I'm just given one node, there might be a lot of defects possible. This is a transistor defect, this is a open defect, this is a port bridge defect, and this is a port open defect, and this is a bridge between these two nets. Okay, this is again transistor on or off defect. So at this one metal layer you are seeing these many connectivity from this. How long, if it will be a huge design, what might be the possibility of number of defects? So you can understand whatever the fault equivalence, fault collapsing we are applied, it might not be a sufficient. Okay, we need to use more vectors and more number of fault classifications to detect all the possible faults. So here you can see, right, what is the chances of your capacitors, and these values might vary or give a different value, the fault might occur. So even you can see here, like another advanced fault models is like, now previously we talked about like within the cell, like similarly, like you have a two different standard cells and it has an interaction between that, then you can see one cell, okay, neighboring faults, you can see like one standard cell has a bridging fault between another standard cell. So when we are going to the cell level test, it's only a internal to the standard module, okay, or standard cells. But even in the this AFG, it's like advanced fault models, we can use the cell neighboring, okay. So this will find out the intracell defects, not only intercell defects, it's intracell defects, and targeting the bridge defects between the adjacent cells, and requires the design layout information and UDFM file creation. All this information is needed because you want to analyze each and every internal to the standard cell faults and bridging faults. And another one is this is interconnect bridge and open. So there is a metal layers, you can see, right? This is one standard cell metal layer M1 and another standard cell metal layer M2. So when you have this distance, okay, actually this is a critical area, we will tell. When this area is very less, you might have a probability of getting the defect. Okay, there is a bridge might happen between these two. Okay, the chances of bridging happening between this M1 layer to M2 layer, M1 is more chances because the critical areas. Now you can understand how the ATPG or the DFT engineer will do. They will calculate the critical area between each and every net, every metal layer, and they will understand, okay, I'm using a 5 nanometer design. What is the minimum threshold I can keep a gap? If that gap is not there, there might be an occurrence of chance of the bridging defect. So I will analyze what kind of these kind of possibilities might be there in an entire design. Okay, let's say this is not within the threshold, there is no fault might be here. So I don't need to test this. Okay, but there should be a occurrence of chance here. So I need to test this. So this kind of all bridging, and you can see here due to them some of the malfunctions or whatever the manufacturing wise we are doing the standard cells, it might have some of the opens, this interconnect opens also might happen. So these kind of faults also we can able to test by using this advanced DFT fault model like interconnect bridge and interconnect open. So what else? So these are like still we discussed like, okay, open and bridge. Let's say previously we discussed about the delay faults, right? Slow to rise, slow to fall. But now path delay fault modeling. What is path delay fault modeling? So there is a input you are giving here. You are not expecting output here. Okay. You are expecting an output after some time, after traversing through so much of combo logic, and you are expecting output at here. So that means here this might work here, and here if you give input here it will work. But what is the guarantee when you are giving a input at this node and it is reaching at output of this node? So that means you need to test this complete path, correct? So this is the path delay fault modeling also. Okay, so I can tell you one more example. In order to detect a fault at here, okay, for example, this is stuck at 0. Okay, I want to test this stuck at 0 means I need to apply input 1. Okay, correct. So to get a 1 here, there is a 3 chances. I can give a 1 through this path, or 1 through this path, or 1 through this path. What will do this ATPG techniques or tools, right? It is very lazy. Why I'm saying this lazy means, as a DFT engineer, we always saying like I want to less test time, less test vectors, and I can able to detect all the faults, right? So because of that principles, what they will do, this path doesn't have any combo logic. So the tool will take and give a input from this. Okay, the one will go and reach through this. So that means what you are saying, as a DFT engineer, you are enabling only testing this path, and make sure you are saying I'm giving a 0 here, means I'm testing 0 of this node because of I'm providing 1 from here. But in a functional wise or a structural wise, there is other paths also connected to this one. Are you able to covering this path, or are we able to covering this path? What is the guarantee this path and this path is also covered? We don't know, right? That's why in the traditional approach, they will follow this one. But in advanced approach, even we will take the critical paths also. That means the highest paths, longest paths. So that complete path is able to give the required input or not. That's where we are using the path delay fault modeling. So there might be a chance the defect might happen here, but when we are using the traditional one, this will cover this, and we are saying, okay, I was able to test this one. But when you are sending this chip to the customer, and he will come, I'm using this chip in automotive application, and my airbag is not opened. Because of that, it's gone. Is it acceptable? No, right? So when you're using this path delay, you are covering this. When there is a fault here, you are saying like, okay, because of this fault, it is detected, and this chip is defective chip. I should not send this to customer because this is a defective chip. If someone is using this one, it might be a life threatening. Or if someone is using any medical device, it will not give an accurate results. Or someone using in your mobile, it will not calculate properly. Or someone using in your some of the gaming, it might not provide a proper graphics, right? So these are the chances. Like other possibilities also, the DFT approaches will done in an advanced way. And I think, is this sufficient whatever the till now discussed? I don't know. Maybe even furthermore is there. What is that? Is a timing aware ATPG. Because the same example you can take, right? So usually we will follow this approach by using the shortest path. Okay. So when you are applying the timing, means, let's say I can able to, I use 1 GHz, okay, or 1 GHz of frequency. In that case, it is easy to send the input from this flip flop 2 to this flip flop 4 by using this path 3. But in a functional wise, when you are running at a high frequency, you always try to close your timing. You are able to achieve your design to test this longest path. Okay. When you are always targeting this longest path, means you are very, very guarantee saying like, if I was able to get the required input of this flop from this longest path, means this path 2 and path 3 already is covering with this. Because if I was able to receive the input, required input from this much long, means this path 2 and path 3 is very small one. Okay. If you are able to get a coverage of 99, you will not bother about 80% or 70%, right? So that's why this longest critical paths we need to target always using the timing aware ATPG. Okay. So here I just given an example like, this is a non-critical path. What is the non-critical path? This path 3 and path 2 is a non-critical path. Whenever there is a small delay defect is there. This is a defect. Okay. What is the defect? It is a very small. Okay. This is the duration of the defect. So when you are using this shortest paths, okay, non-critical paths, what will happen? You might think like, okay, even though this delay defect is there, but your response will pass because this delay will not impact when you are using this path. But the same defect when you are using the longest paths. See guys, here is the longest path. When the moment you are using this longest path to test any defect, you are using this small defect might caught. Correct? When you are using this longest path, because of the small delay, you are unable to complete your operation within 1 clock cycle. You are crossing 1 clock cycle. That means you are not getting the expected output at this place. Then you are saying, okay, there is a fault in this longest path. That means this chip is a defective chip. Okay. So when you are using a traditional one, it will pass. When you are using a transition, it will pass. When you are using cellular, it will pass. When you are using the interconnect bridge, interconnect open, it will pass. When you are using the even previous technique, whatever we discussed, this path delay, it will pass. See, these various levels it is passing. Okay. And when you don't do this timing aware at APC, you are saying my IC integrated circuit is absolutely fine. I can sell it to the customer and I can make it a lot of profits. But the moment if you do a timing aware ATPG, your chip will identify it is a defect and you cannot send this as a defective chip. So now you can understand how can we reduce the DPPM values, defective parts per million. Okay. So each test, guys, till now we discussed so many that Stucket and TDF. It might give 100 of DPPM. Okay. And it might be using a delay faults. It might reduce the number of faults. And if you use the path delay, it might further reduce. If you use this interconnect bridge, layout or internal transistors, everywhere you found fine. But when you're not doing the timing aware ATPC, there might be a chances even further small delay defects might failure. Okay. So I will give you a small example how it is reducing my DPP. So when I'm using the cellular test, Okay, my DPPM is reduced from 2000, like 250 to 200. So like it's some 50 defective chips I can able to detect by using this cell-aware test. So when I was not using the cell-aware test, basically the stackgate and transition faults like the AND gate and OR gate I detected, right? From there I can get 250 defective parts. Okay, that means 250 defective parts means 250 parts which is escaped from the defect and sent for customer, not like defective chips. It is a faulty chips, but we are treating as a passing chips. Okay, but when it comes to cellular, we are able to reduce 50 such escapes and we are able to identify. But when you are using this automatic fault grading, like the interconnect opens and bridging faults by total critical area and whatever we discussed, right? So this kind of fault analysis, even our further DPPM is reduced to 150. That means still further we are able to catch another 50 or 60 kind of defective chips to the customers. We are not sending, okay, but still we are sending something around some 150. We don't know. There is a chance. So after you are using this timing aware ATPC, your DPPM is reduced by very like a huge amount, okay, 100. So understand guys, like when we targeting the zero DPPM, what kind of approaches we need to do furthermore, how it is possible. I can say zero, exactly zero DPPM is impossible, but how to try to reach a near zero DPPM, that's what our target, right? So we should always enrich and always think what kind of, see, when we are following the traditional approach, we don't think about this path delay, we don't think about this internal to the standard cells also, internal to the transistor level also fault might happen. We don't think like even high speed conditions this timing aware faults might happen, we don't think, right? But later, because of the learnings from the various manufacturing analysis and all, we are thinking beyond that, right? So like that we can further reduce the DPPM by using these techniques. So that's what actually the basic, or you can say like some of the advanced DFT techniques we can use for any kind of real-time industries. Okay, what was the other techniques to reduce the test time and cost? Okay, so I told you the scan chains. Okay, this is a small 1 or 2 slides I will explain because this is something beyond the internal concepts. But what is the scan compression? So because when you are stitching the scan chains, it will be huge length. You some for example, I have some 500 flops. Okay, so something like I have a 5K flops. Okay, so in the 5K flops, that means my chip has 5 inputs and 5 outputs. Okay, so that means I can make this 5K flops into 1,000 and 5,000 scan flops, scan chains I can stitch. You can take this example only. Okay, so that means 1,000 flops in a chain means when you want to shift your vectors or patterns, you need to apply 1,000 clock cycles to make sure you are applying the input of for one scan chain. Okay, like that you need to give for all the scan ins and scan outs huge number of shifting cycles you needed. Guys, remember how many shift cycles you are using, that much time it will take your testing. So how can we reduce the number of shift cycles and testing time? So that's where this concept came, like a compression, scan compression. It's a very advanced technique. We can say like this compression techniques everywhere, like not only the scan, so many times you might use. So this compression might be like easy. We can use the same scan ins and scan outs, but internally we will use the decompressor and compressor logic, and we will make each chain into a small, like let's say the 5K I made a like 1,000 is 1,000 flops in one chain, right? So I can use a scan compression ratio of 10. 10 means each chain of 1,000 length I will reducing to 10 internal chains. That means this single chain is converting into 10 small chains, each one is length of 100. So now you can understand like that this 5 into 50 scan chains will come. So this 50 scan chains will have only 100 scan flops in that. So when you are previously shifting a one scan chain, you need 1,000 flops. Now you need only 1,000 clock cycles. Now you need only 100 clock cycles. So what was the ratio you are reducing the test time here? So 100 clock cycles to 1,000 clock cycles to 100 means almost 10 times you reduced, right? Okay, so that's where. But you can ask a question like, why can't we go with compression ratio of 100? That means even this 50 like chains can be converted as a 500. That time what will happen? There is a trade-off always, you can understand. If you make further less means, if a 10 is your scan chain length means, you can understand the number of flops in the scan chain is 10 means you might miss the controllability and observability of some of the nodes because of higher compression rates. So we always, as a DFT engineer or a architect, you should think like what is the optimal compression ratio means making a bigger chain into smaller chain. What was the ratio you should follow? That ratio should compromise your test time and runtime, but it should not compromise with respect to the controllability and observability. That is the only point here. So this is the compression ratio, like the number of internal scan chains by the number of scan chains we have. That is the compression ratio. Basically, till now, whatever we discussed, right? So in a real-time manufacturing, how it will be tested, this is everyone might know how the automatic test equipment AT ways, how we will do. Let's say this is your circuit under test means here you will keep your IC, okay? Whatever my fabricated IC, integrated circuits, I will keep here. And whatever the till now we discussed, right? That different techniques, fault models. With that, we will generate the different vectors, okay? That is called patterns, okay? And when you are generating the patterns, we will expect the what is the expected output also, right? That is the expected response also. That means my vectors will consisting the inputs and expected outputs also. What we will do, that inputs we will apply a circuit under the test means in that ATE. I have showed a lot of real-time examples also in the previous session, how we will keep an SOC under the ATE. Okay. So when you keep the ATE, you will apply each and every vector. Okay. When applying these vectors, your circuit will give a response, correct? So these responses you will have again in the ATE vector, you will have a comparator unit. So these responses will be compared whenever you are applying the vectors, those response to the already actual expected response. Okay, this is we already knows. But what is the device is giving? Is it giving expected one? It is a pass. If it is not giving the expected one means it is failed. So this is where everyone might know this is very simple way, but the real DFT engineer understand how can I able to make sure my number of test vectors will be as low as possible. But this complete chip, this complete SOC can be tested without missing any defect is the actual DFT work. Okay. So that's where we are following like different approaches, different scenarios to make sure how much our less patterns, how much is the highest coverage to test all the faults. Okay. So what is one more? Because you might know till now, okay, we are there combo logic, some of the sequence and this and all we are tested. But what about you can ask about memories. Okay. Are we use these techniques, whatever till now we discussed some 6-7 techniques, can we still use for memory based testing? Yes, we can use it, but are we guarantee each and every fault in the memory? Guys, understand memory is a very hard macro. It's a very complex logic there within the memory. You might understand various memories are there. Okay. So let's take an example, static SRAM or any DRAM. So internal to the memory also, can we apply this DFT techniques? I can say yes, we can apply, but instead of that, we have even a further a good techniques. Okay, the built-in self-test or BIST techniques. So those techniques we can use to test memories separately. That's why the till now whatever techniques I never touched anywhere the memories. But why this memory based test is really important? Okay, nowadays any chip, any integrated circuit consisting 40 to 50% of the chip is only the memories. Imagine guys, like your complete functional design is a 50%, but your memory storage element is 50%. Just example, like whatever mobile you have in your pocket, you are saying like you are saying I'm taking a used mobile, like it's a latest configuration. It has okay 256 GB internal storage and 16 GB is RAM. Okay, so that means how much space it should occupy in your mobile. Okay, so you want to keep further increasing 256 to 512 okay GB memory. Still, lot of mobiles came, right? So to do because any small mistake in the memory, your chip will be scrapped and it should be thrown. So you need to do effective testing of memories as well. Okay, so to do the test, I want to give a brief idea of like not only testing, some of the idea like how the memories will be there. Okay, and how can we able to test? Is testing is sufficient? And title is something different I have mentioned. What is that title? Yield. Okay, how yield can increase? Because if you find a defect in memory, how my yield can increase? Anyone knows? I can do a memory repair as well. Okay, so memory repair is very, very interesting concept. Like we can reduce the TPPM, we can reduce the faults, we can reduce the whatever the yield losses also. So how it will be? So before going to test that, I explain that. I will give you an idea like what was the best applications of this BIST. So BIST, it's a like built-in self-test. I think everyone aware. So memory BIST is like to specifically do a memory testing purpose. Okay, so this can test multiple memories in our design, and it can do a diagnosis, and it can do a soft programmable algorithms. We can do lot of tests by using this BIST. Okay, so what is the basic memory? How it will looks? You know, right? Basically, a physical memory will have a different input and output ports. In our design, it will be a plain memory. Okay, but as a DFT engineer, I told I will do a scan stitching, right? But for that memory, I will add a memory controlling logic. Okay, memory wrapper logic. For testing a built-in self-test, I will add an extra DFT logic to make sure it can test the complete memory everywhere internal to the logic by applying the different algorithms. Okay, I told you algorithms. Okay, what is the algorithms? I will not go through like each and every details of the algorithm, but to get an idea, a simple checkerboard algorithm. Checkerboard algorithm means write one and write zero, or read one and read zero. This kind of algorithms we can apply. Okay. And even a March algorithms. What is March algorithms? From incremental, decremental wise, you can write a zero, after that read zero, write one, read one, or even you can see like, see, this is a memory. For example, I can give you, I think we have time, right? So see, let's say here you can write one, and after that you can read zero. Then you can say like, okay, this cell is defect free because I can able to write one and I can write read the zero. And similarly, I can write zero and after that read zero. So this lot of write and read operations we will do within the memory to make sure my every cell in the memory, like let's say if a 32 cross 32 memory is there, means each and every cell in the 32 cross 32 memory can be tested by using the BIST. Okay, so like what is the logic you are going to add as a DFT engineer? We can say this is the functional wise. Memory is just kept for storing some information, but are we sure the memory is really storing the required information and able to capable to store, and whenever you want to read, you are able to read that? Our part. It's our responsibility to test. For that, I'm adding an extra logic. See, this is the memory interface I will add. This is the memory controller I will add. So what is exactly here I'm adding this logic? Is it really required? Means because of this extra logic, my my chip area will increase slightly and my number of gate count will increase. But but what is the impact? We can able to test the memories, each and every memory effectively. Okay, so I just think like what is there in the controller, what is there in the interface, this and all fine. Okay, but how exactly this interface logic will work? Okay, so see, another thing is like we can do different grouping. So I think guys, memory based, I will not go any deep internal to that, but I will just give an idea like how can we do. See, this memory grouping is fine. Like we can do all similar type of memories, all RAMs in one side, ROMs and one side like that. And I want to tell you about the memory repair. What is the memory repair? If any fault in the memory, we can replace that faulty location with the redundant element. So for example, this is my memory. So I will use a spare row. This is a spare row. This is another spare row, or this is a spare column. This is a spare column. Okay. So if any fault happening here, for example, okay, so I can discard this row and I can map this row, and I can say, even though this chip is failed, but this chip can be repaired by using this pair. Similarly, the column approach. Okay. So these are the three types of memory solutions: column repair, row repair, and row and column repair. Like that, we can do any repair. So this is same I was just discussing, right? Left half and right half. If you have two columns, we can use this pair element or this pair element. We can test. Similarly, row, and you can use this top spare row or bottom spare row, and you can test. Similarly, row and column. So the last and final diagram of this one slide is just how the complete architecture. Okay, this is your memories. When you are going to test with BIST, you know which is failing. Then you can see the BIST controller will have the repair information, and it will go and map your failing columns and failing rows, and you will able to repair your memories. Okay, this is an example. Like if any, let's say for example, this column is failed. Okay, then you can use this pair column and map. Thus, you are just mapping that and making your memory is still working like that. Even it is a single column, so you can make sure like that. So this is where we can reduce the yield. Okay, whatever the defect we are finding, that we can able to detect, and we can increase the yield, and we can reduce the test cost and test time, and we can make sure our DFT is effectively reducing the test time and test cost, as well as without compromising any defects. That's all. I think within the time I can able to complete. Yeah, I have some time for Q&A. Please go ahead.
Okay, sir. Shankar sir, thank you very much for yet another good session from you. Dear participants, I hope you have enjoyed this session too. Now the session is open for queries. Any questions from participants? Please go ahead.
Okay,
Yes,
I think
please.
everyone got a very clear idea, or no one got any idea.
Okay, if there are no questions from any participants, I think let us close this session because it's already 5 p.m. and we have one more session, that is the last session of this FDP from 5 p.m. to 6:30 p.m. Already Dr. B. Gopi Krishna sir has joined us from Oman. Hi sir.
Hello,
Welcome,
sir.
welcome.
Thank you, sir. Thank you.
Okay, Arpita ma'am, please conclude this session. I will go ahead with the next.
Thank you, Shankar Rao sir. Thank you for the wonderful session. We wish to have you again in our future programs also, sir.
Okay, ma'am. Thank you.
Thank you for
Thank
sharing
you
your
so much.
valuable expertise with us.
Okay, ma'am. Thank you. Thanks for this
Thank you.
opportunity. Thank you, Srinivas sir. Okay.
Okay, thank you, Shankar sir.
Thank you, sir.
Okay, now before we start the final session of this FDP, small information regarding online test that is going to be conducted today. As I already informed you yesterday through this Teams meeting and also through the WhatsApp messages and mails, my dear participants, there will be a test today from 6:30 p.m. to 7 p.m. with 20 objective type questions, that is MCQs, multiple choice questions. Time allotted will be 30 minutes. There are two ways you can attempt this exam. Number one, we have already scheduled the exam in the Atal portal from 6:30 p.m. to 7 p.m. and the portal will be locked after 7 p.m. Please note this point. Second option, there is every chance that Atal portal will be busy and may be hanged. because so many other Atal FDP online programs are going on. If all at once attempt to log in the portal may be hanged. Then we will share the Google form at the same time at 6:30 p.m. in the Microsoft Teams chat box and also in the WhatsApp group. You can attempt the same test for the same half an hour time for same 20 MCQs using this Google form also. The difference is if you write your exam in the Atal portal, if the portal gets accessible, you can directly see your marks there itself and they will be saved there. Or else, if you write the exam through the Google form that we share at 6:30 p.m. and your marks will be recorded at us and we will post them. We will upload your marks in the Atal portal within 2 days. That is, by Monday or Tuesday, we will post your marks and attendance information in the Atal portal. After Tuesday, if you satisfy the eligibility criteria of the Atal Academy instructions, that is 80% of attendance in the online sessions, 70% marks to be scored in the exam that is going to be conducted today, and you have to submit feedback in the Atal portal in your participant login. Then you can download your participation certificate from the Atal Academy portal itself. Post Institute will not issue any participation certificate, please. I hope this information all you people knew. And only thing is I want to once again convey this information regarding the online test that is going to be conducted immediately after this session from Dr. P. Gopikrishna sir, Professor, University of Technology and Applied Sciences, IBRA Woman. Once again, a warm welcome, sir, to our online Atal FDP program. Thank you for sharing your, spending your valuable time with us for the next 1.5 hours.
It's my pleasure, sir.
Arpita ma'am, please
sir.
introduce sir to this meeting. After that,
Yes.
Gopikrishna sir, you can share your slides after brief introduction.
Okay.
So before moving on to the session, I would like to introduce the distinguished speaker of this session, Dr. P. Gopikrishna sir. It gives me immense pleasure to introduce our distinguished speaker for the session, Dr. P. Gopikrishna sir, who is currently serving as Professor, University of Technology and Applied Sciences, IBRA, Oman. He has over 22 years of teaching experience, along with he has also completed his postdoctoral research in the USA. A chartered engineer and fellow of the Institution of Engineers, he has earned numerous accolades, including the Oman Chamber of Commerce Industry Innovation Award, over 10 best research paper presentation awards, 3 funded research projects worth $20,000, and multiple best staff awards also. He has guided over 40 student projects, many of which have received national recognition. With 32 research publications, 6 patents, and 4 authored textbooks, he serves on the editorial boards of 4 international journals. His core expertise lies in Arduino, microcontroller programming, MATLAB, and intelligent systems such as neural networks and fuzzy logic for electrical and computing applications. He has held leadership roles including principal, professor, project coordinator, and university exams expert committee member. Passionate about student-centered learning, he actively conducts workshops, seminars, and short-term courses on cutting-edge topics like Arduino and Raspberry Pi-based innovations. We are truly honored to have you for this session, sir.
Thank you. Thank you, ma'am.
Sir, kindly share your presentation and continue with the session, sir.
I already shared, ma'am. Are you able to see my screen?
Yes, sir. Yes, sir. It is visible.
Yes, sir.
Yes, sir. Yes, sir. Now it's
Thank you, sir. Thank you. Good afternoon, everyone. Today, I would like to share my knowledge related to multimodal deep learning approaches. And here, as our FDP is focused related to the semiconductor manufacturing industries. Therefore, I have taken problems related to the VLSI, and we are going to apply multimodal deep learning approaches. So what we are going to cover, the first one, we are going to cover about the first introduction to various AI techniques. particularly we are focusing related to the deep learning. Deep learning, nothing but artificial neural networks we are going to use here, which are the advanced versions of AI. Already we know AI under the AI ML, under the ML DL, deep learning, under the deep learning GPT, so all it will come. No? So you know that one. So we'll discuss about that. And if we classify the deep learning method, the first one is related to the classical deep learning methods. And what about these methods when we need, we'll discuss. Next, advanced deep learning methods related to recurrent neural networks, convolution neural networks, and other things also, other advanced also is there, but we are focusing related to these two. And we are going to take some problems in the VLSI manufacturing industry. And if you are able to overcome those problems, definitely we can enhance the productivity of VLSI manufacturing industries. That way we can able to use. So what are the issues we'll discuss there? And we are going to apply deep learning methods with respect to classical and with respect to advanced. From here onwards, number 5 onwards, we are going to go purely practical based. I will give the live demonstration by running the programs in MATLAB and also Python. Both may be better to know. That's why we are using both MATLAB and Python. So proposed system, that is multimodal deep learning, in what way it is superior compared with the existing deep learning methods we'll discuss here. And what are the future directions and the research opportunities in the VLSI manufacturing industry, that also we'll discuss here, and thereby conclusions, references. So if we have the overlook about the different AI techniques, and we are particularly focusing on neural networks, not on machine learning, that is deep learning networks. The first one is radial basis function neural network. It is a best function approximation technique. When we will use this one, we'll discuss. Next, backpropagation neural network, also called as multi-layer perceptron neural network. And hybrid intelligence systems, like we are going to add fuzzy logic with the neural networks, that is called as ANFIS, Adaptive Neurofuzzy Inference System, one of the most powerful deep learning technique. And fuzzy logic system, genetic algorithm, support vector machine learning, different AI techniques are there, but particularly today we are going to focus only on this deep learning methods. So before going to start, just only to give an idea, within 2 or 3 minutes, we'll try to complete. So neural networks, which is considered as deep learning. Nowadays, these are the most popular one. All GPTs, chat GPTs, LLMs, everything they have been developing and creating a revolutionary environment nowadays. Therefore, it is better to know the basics of neural networks. Therefore, whenever we are going about the neural networks, we'll generally ask what, why, where, how. So what is neural network? So network means interconnection. Neural network means interconnection of several neurons. And the neurons we are classifying into total here 3 layers. In each layer, neurons will be there. So these are called as input neurons here, input neurons 1 to n. Similarly, output neurons also need not to be a single output, maybe a multiple output also. In between input and output, we can have the hidden layer. Maybe hidden layer 1, hidden layer 2. It depends on the complexity of the problem. So what is neural network means? Interconnection of several neurons. Here we can ask what is a neuron here? A neuron, each neuron is a data processing element. That means if any data given as an input, it will process the data to all other neurons. See, every neuron has connected with other neurons. It is just like our human brain, that is called as biological neural network. And whatever we are developing in the system, it is called as artificial neural network. Only based on these concepts, only the GPTs, ChatGPT, LLMs, all they have been built up. So this is about neural networks. So why we need to study about the neural network? Whenever I am giving a seminar, I used to quote this quotation, Albert Einstein. He has given one quotation: as far as the laws of mathematics refer to the reality, they are not certain. They are not certain. And so far as they are certain, they do not refer to the reality. What it does is, this statement is indicating that if we see our technological things developed, how when our professors was developing, even nowadays also, we are developing based on the mathematical models. Any technological things, generally we have a complex mathematical models. But when we observe the complex mathematical models, there are several assumptions wherever we feel difficult. For example, we are considering a signal with a certain frequency, but a signal is not one particular frequency. It is also have the disturbance log noise. We are just neglecting the noise frequencies, and we are only designing the system based on one frequency. But there are other frequencies we are neglecting. We are unable to model that one. Therefore, it is not 100% accurate. And whatever the mathematical modeling, that's why this all mathematical modelings we will call as a theoretical. And when we compare theoretical and practical, even if you do a laboratory, there will be error, maybe 20%, 30% more error will be there. But whereas instead of depending on the theoretical background, if you are depending purely on the practical background, the error percentage will be reduced. This is why we are going for the neural networks. In the neural networks, more is the practical data we are considering, and less is the theoretical. But whereas in the mathematical or simulation softwares, simulation circuits, right, we are developing based on the mathematical, and we are feeling that those are accurate. But in reality, the error is more. That's what we need to understand here. Therefore, whatever from this statement, we can understand that mathematical modeling of real system is an approximate to the reality, because we know the mathematical models, they have been developed based on the several parameters, several complex things, several assumptions. With that, those are only approximate. Okay. So that's why I told that I'm telling that the best way is intelligent techniques. When we are using the intelligent techniques, less is mathematical and more is the practical. So if you come to the applications, there are n number of applications. This was almost a very old slide, but at that time, more than 20 years back, I have just created. At that time itself, I have written. Now we know everywhere, every part is a AI. Therefore, there are n number of applications here. And how neural network will be used. In order to understand the neural network, we need a practical data, right? The practical data, generally it is consisting of input data and output data. Input may be a multiple input, output also may be a multiple output. For example, in order to understand, I have taken a sample data, because for a neural network implementation, we need to give the data as a food. So we are collecting data, so input and output. And if you give such data, it will train with the training data, whatever this one data we are giving, it will train. Once it is trained, and if you give the new data, which is not available in the training data. See here, this is the 2. But see here, 2 is not there. Here 2.5. See here 2.5 not there. That is a new data. Then it will automatically give the output. See the output here. Output from the neural networks. We have not mentioned for the new input what is the output, but neural network is the calculator. That what happening in all the GPTs. Once if you train the system, it will understand what is the pattern recognition, or what is the relationship existing between input and output. And if you give the new input data, it will give the exact data. That's what the chat GPTs all they are creating based on the training data we have given. So to understand better, first we need to take a simple model, not to go for a complex model. A simple model, a linear model I have taken here. And first we are going to apply on a classical deep learning methods, that is radial basis function neural network, and backpropagation neural network, and adaptive neural fuzzy inference system. These three calling as a classical deep learning. Why classical means when we can able to apply these methods is whenever we have a table data like input and output, then we we can apply these methods. That means for modeling, we are doing mathematical modeling. No? That is a more error, but whenever we have the table data like input and output, we'll use these methods. And the radial basis function method is a best function approximation method. And backpropagation neural network is a multi-layer perceptron model. We'll apply for a complex, whenever we have the more data and complex patterns, there we can apply. Adaptive neurophagy inference system is a more accurate system because we are going to combine the neural networks and fuzzy logic concepts, hybrid systems. Let us see about these models. So first here I'm discussing about a MATLAB. We'll also discuss same thing in the Python also. So in the MATLAB simple program, so X and Y are the training inputs, and we are just specifying the goal. What is meant by goal means whenever training is taking care, how much error, training error we need. Maybe generally 10 power minus 3 also enough. So if you want more accurate, that you can able to increase. And this is important in the spread. How we know spread is 2.24. Initially, we'll train with 1. And this is all based on the trial and error method. Trial and error method. We don't know it is the best spread we have to select. What is the spread means? It is when we mention the data, input and output, how input and output is spread over the space. This is the spread. We don't know what is the approximate set. Generally, the difference between one input and input like that also we can approximately estimate 3 minus 1, 2, so around 2. But the exact value 2.24. If you keep 2, we'll get some around 98% accuracy. If you get 2.2, 99. If I get 2.224, then I will get 99.99% of accuracy I can able to obtain. So just only this is the program. See in the program, number 1 input data, number 2 output data, 1, 2, 3, 4, 5, and this is the main keyword. New RB, that means neural network radial basis function. We are passing the parameters input and output, goal, spread. MN means number of neurons. DF means display. When it is running, every neuron, every epoch, it will display or not. If you keep 5, every 5 it will display. A simple program. So MATLAB program. Just only this one. In the place of X and Y, you can give any semiconductor manufacturing related data. We'll see the live demonstration. I will show. So just remaining all same only. And come to the backpropagation neural network. This is also same patterns X, Y, and this is a new FF function, MATLAB function for feed forward neural networks. And a number of epochs 50, goal, and you can try this one. And adaptive neurophagy inference system. This is also X, Y, and it is a fuzzy membership function we are using, GWell. Different membership functions are there, Gauss membership function. We can change if you are not getting the accurate results. So we can change these parameters. We can increase or decrease, and we can change these parameters. And this is the ANFIS. And if you want to get the evaluations, we can use this command here. See, when we have used this one, when we have trained, we have given, see how we have trained, we have given odd numbers we have given and corresponding numbers. But in the program, nowhere mentioned y equal to mx plus c, like that we have not mentioned. Just we have given a practical data. And when we train, it will understand. And after training is completed, that means if you are getting the accurate results, now I'm giving the new data, which is not there in the training data. See, these are all even numbers. But if you observe the training data, odd numbers are there. But in the checking data, I have given the new data. For new data, this is actual output. In my hand, I have. But what are the radial basis function? It is giving 5.0, and back propagation it is giving 5.03. But see here, ANFIS it is giving 5.5. Exactly 5 it is giving. So like that, see the results. So this is the beauty of the neural networks. For simple problem, it is giving easily. Even for complex problems also, if you if you give the data accurately, definitely it will understand what is the relationship is existing among input and output, and it will give the prediction values, forecasted values. Now, now let us go to the advanced. What we have understood is classical deep learning methods. The classical deep learning methods here, we have discussed about radial basis function neural network. It is a best function approximation method, and backpropagation neural network, multi-layer perceptron for a large complex models we can use. But here, not to expect 100% accuracy, we have to expect around 95, 96 only. But here we can get a 100% accuracy. That's why I see the differences. Here also we can get 100% accuracy. Because backpropagation neural network is having certain limitations. That is, it will converge. That means it will stop with the local minima. So that we need to adjust the learning factors that we'll see in the live demonstration. So classical learning methods. Now let us go to the advanced deep learning methods. So in advanced deep learning methods, the first method we are using the recurrent neural network. Why we need this neural networks? When we were doing the research around, I have been in this deep learning methods from last 25 years. I have been working. At the time, there is no this type of advanced deep learning methods. I used to apply radial basis function networks for time series predictions. That means for stock market predictions, for weather predictions, for load predictions, which are time dependent, time sequence dependent. We are using. Sometimes we used to get the accurate results. Sometimes we are unable to get the results. And we tried with the gold predictions. Sometimes we were not getting. At that time, we felt difficult. But when this recurrent neural networks, it came available to public, then when we started using even exact or almost on accurate results, we can able to get. You can see here what way we can use is time series predictions. Even we can use for our voice recognition, handwritten recognition, but mainly time dependent. Time dependent. All neural networks are basic structure, but what is the main difference is these are the hidden neurons, hidden layers. Within the hidden neurons, data will sent back. That means the previous state, it will store in the memory. In before cases, just we are not remembering the previous state, keep on processing the data in feed forward neural network. But here, the previous state, but for example, this is at 10 minutes time, and this is 9 minutes time. So when it is processing, 9 minutes, what happened? That previous time step it will remember. That's why the type of recurrent neural networks we'll call as LSTM. The most popular RNN is LSTM, long short-term memory. That is a time series predictions. So using this recurrent neural network, if we have the data and it is having the time like stock market or weather forecasting, any load forecasting, even in the VLSI manufacturing, we have been creating the chips with respect to different timings. So whenever any time dependent is there, that also it can able to predict. I have applied. I will to the VLSI problems. I will show the results to you. So this is the first advanced deep learning methods. The another one is a convolution neural network. All neural networks basic structure is same, but in the convolution neural network, here the main focus is related to the images. That means face recognitions, data object identifications, any image processing. So when image processing is going on, these are the convolution layers like a book paper by paper, no? So it will scan each part by part in the layers so that it will extract the features, and those features will be given to the neural networks. So that type of technique is going on, and this is for the image processing applications, all image processing. So in the VLSI manufacturing, when we made a ready of any IC, is it, for example, we have printed on the top of IC, the IC number we have printed. For some ICs, maybe printing not happened. So those ICs will be identified, and it will not go to the customer. It will be identified, and it will come out from the process. Like that also, we can able to use image processing in the VLSI manufacturing industry. Manually identifying in the millions of ICs is difficult, but it will identify in the VLSI manufacturing. So CNN, convolution neural networks, is related to the image processing. And let us come to the what are the problems existing in the VLSI manufacturing industry. If you are able to identify those problems, and definitely it will be helpful for the enhancement of productivity in the VLSI manufacturing industries. As we all know, we have come across 6 days related to the semiconductor. So first part, IC design, mask, manufacturing. In the manufacturing, this is the main part. No? Here, what type of fabrication, wafers, in the IC, dicing, all packing related, several process it is, total the process is going on. So problem maybe in the design case or mask case in the manufacturing, but here mainly we are focusing on manufacturing, enhancement of productivity in VLSI manufacturing. Therefore, I have taken wafer images and yield things, data, so that we can able to identify the yield capacity and enhance, we can able to improve the productivity. So how it will be happen, we'll show that one to you. For example, here we want to discuss about the yield. Maybe I just saw your schedule. In that our resource persons, they have explained to you clearly about the yield. So as we know, it is a total refer. So in that, each square block is related to the IC, right? So all red colors, sorry, all yellow colors are a bad one. So 18, and good is 10. So out of 28, so 10 by 28, if you calculate how much yield we are getting is 35.7%. So this much yield is not a good yield, right? So yield means how many ICs in a particular say it may be a 20 centimeter. That means 200 mm vapor is there. So now let us see here another one. Here the bad one are 33 and good one is 103 and total 136. So yield is 75. Now, if you see the another one, the yellow part is reduced and yield is 94.2%. Therefore, this is a good one. So, in the manufacturing industry, we need to identify the best yield for a particular wafer, how to identify the best yield. So, for that purpose, we are going to apply the various deep learning methods, and we'll identify accordingly, we'll process. Okay, so we are going to identifying with manual inspection or some any other things. It will take a time, but with respect to the neural networks, it will within a less time it will identify. Now let us see the things to apply to study to solve this type of problem. So I have taken a data sample. I have downloaded a data, sensor data, and it is having total 500 total data samples 1567, and these 592 are different sensors data. So this type of data I have taken, and we will clean that data And at the last column, total 591 futures. No? At the last column, -1 indicates pass, +1 indicates fail. The first one is a timestamp is there, that also we have used for RNN. So this data we can able to get from this web link. So let us what we are going to. So we are going to apply our classical neural networks models. First, we will apply the radial basis function, backpropagation, and FIS in the MATLAB environment we'll mention first. After that, same we can also apply in the Python, because sometimes Python will be very faster when our complexity is increasing. So both, whatever the environment, I'm going to give all the codes to you. So let us see the thing. So all these programs I will share with you now. You can practice for your master level projects, bachelor projects, even for research projects. So here we have the VLSI data. So this is the data we have downloaded from that site related to the VLSI manufacturing industry. And you can see the in first column timestamp is there. So remaining from here, it's 0, 1, 2 like that. The last end, if you see here, 589. That means 500. 0 no started. So 590. And this is 591. So total 590 sensor signals it is getting. And the last one is, you can see here, -1. -1 means pass, +1 means fail. So all the data. So this is the data we have downloaded related to the VLSI manufacturing industry. So based on this data, now what we are going to give is, so I'm going to take a radial basis function neural network. Radial basis function neural network is only just a 5 lines code. And if you want to read the data from the Excel file and you want to plot some extra lines we are adding. That's why I'm sharing these all codes with you. Before when ChatGPT was not there, in the MATLAB we used to write everything automation, and we used to sit for one day, 2 days to write this much code like that. Now only matter of 5 minutes with the correct prompting. If you give the correct prompting, it will give ChatGPT will give the coding. Anyhow, we need to solve the problems. See now same code. We just whatever we have described in the presentation, same code only, input to output to training patterns we have given. So just if you run this code, you can see now it is running here. We don't know what is exact spread value. That's why I have given multiple spreads, and it will compare and it will finally give the results with respect to the best spread. The spread, changing the spread is nothing but training. We have to train, no? So training, the training means which spread it will suit exactly. That what we have to train. Once trained and you got exact values, then no need to train once again. We can fix and it can able to predict. So it's keep on training. Spread 0.8 here you can observe. Root mean square, and it is taking spread of 1.5. Comparing the root mean square with respect to all spread, so that finally it will identify the best spread. So finally it is identifying chosen spread is 0.5. So when it has chosen 0.5 and it is giving the out. Here you can see the blue one is actual and the red one is predicted. So you can see 1 and 0.95, almost all it is matching. Okay, so let us see the results. Let us see the results here. So actual and predicted. And what is the prediction accuracy we got? 95.42% we got. Before in my presentation, I have taken y equal to mx plus c. Simple data we have taken for better understanding of model. Now this is a complex problem I have taken. How I can say it is a complex? See the data sample. The very large data I have given. Even though if you have given large data, it is understanding the relationship existing between input and output, and finally it is saying. So how much, what I am doing with this one, I am going to predict how much yield, how much is the yield. 95.42% is the yield. Then how much loss from the wrapper, how much is the loss? Only 4% only. So that means it is a good. Whatever we are getting 95% output chips from a particular wrapper. Therefore, it is a good one, 95. Because I already trained. Initially I got 80, 60, something like that. But in the training parameters, I have changed and I have reached to this part. Initially, just some 10 minutes we need to train, spread number of neurons. Those things we have to. Now, if you go for the back propagation, all these programs will be shared with you. That's what images when I uploaded, it was 2.5 GB. It was taking a time. That's why in the MS Team I will share without the images, and I will give the Google Scholar link also. So all these programs will be shared with you, so that you can further do experiment and research. Most useful for ready-made projects. It will be useful. Okay. So now let us go for the. So how much we got? 95.42. The same program I have also implemented in the Python. So here you can see the Python RBFN code. You can see RBFN code. Same code only, same logic only. Just install this one, and all this code also I have shared. Why I'm sharing? Okay, we'll get from the ChatGPT, no? But to do all the things, it may take time. Now I am giving ready-made, just for a study purpose. Once if you have understood, then you can go ahead. Just if you run this one, already I ran this one. Okay, so actual and predicted, you can see here 1.0, 0.98. And how much is the accuracy here? Accuracy I got 95.37 in the Python. Same code only, same Excel file only I have given. When I have used it in MATLAB, I got 95.42, 95.42. The Python 95.37. Anyhow, 95 it is matching. Okay, so environment is the different. And similarly, if you go for the back propagation. So these all things I will close. Now I will run the back propagation here. Oh, this one is back propagation I run. Sorry. Yeah, back propagation selected. Yeah. See, this is the back propagation neural network. You can see the actual and predicted, almost all very nearby one only. How much accuracy we got here, back propagation? .25. Initially, I got 88 to 85, but I changed the number of neurons, type of function. Little changes I have done, so that we can able to increase that one. See how much non-linearity is existing. See the data file. It is not a linear relationship. Almost all 590 sensors, it is giving the data. This all data related to temperature, pressure, color, so many things it is giving. They have not mentioned there, but they just mentioned only the sensors data. That much non-linearity is existing, but see the accuracy of the result, 95 point. Similarly, the same thing, if you run in the Python program, BPNN, here, this is the one. So already I run this one. So you can see here, only to save the time. If it is a like workshop, if you have the time, and you can have the hands-on session also, same programs you can able to execute. But as I'm sharing the programs, one time you can test only, it will take. Now here 91.56 only we are getting in the Python program, but whereas in the MATLAB we got 95%. So that's what. Similarly, if you go to the ANFIS, Adaptive Neurophagy Inference System, this is the most powerful one. So how much accuracy we got here when we run the ANFIS? No? Let us run this one, ANFIS. We're starting the ANFIS. Only 5 lines of the code. Don't think that this program I have given almost more than 100 lines of code is there. It's all only just to read the Excel file and plot those things only. The main concept is just only 1 line or 2 lines. Even in the Python also same. As ANFIS, no, it will build up a big neural network, and it will take time because I am running here. In the meantime, this is about classical neural networks. No, now let us go for the advanced neural networks. What are the advanced neural networks? Advanced neural networks are related to recurrent neural network, convolution neural network. Recurrent neural network based on the time dependency. That means time series. And convolutional neural network based on the images. Both let us run. So for time in the Excel file, time is there. Time dependency is there. So we can able to use the same file for recurrent neural network. So I'm using Python only because as these are the advanced versions, we need a big processors. Even in the MATLAB also we can run, but Python will be easy for advanced one. So I'm going for a RNN here. This is the RNN. So for RNN, the same data file only I have used. See here, multimodal deep learning, VLSI data, and UCI secom -CSV. That is the file. No, you can see here. What is the file name? This is the file name. If you just right click, copy as path, just right click, copy as path. So that file is copied, and go to the Python program here and just paste here. So I already pasted here. See, I'm showing pasted, and I just added R because of that some error is coming because this is a backslash. Actually, it is a forward slash. To suppress that one, this R they just added. So this is the file we are reading. So that means our Excel file we kept in the somewhere else folder. Now from there it will read and it will classify the data. And the structure is a current neural network programming is there, where we have to make modifications is number of epochs, number of hidden layers, number of hidden neurons, type of activation function. These things we need to make changes. And once if you run this one, it will take time of 2 to 3 minutes. Already I run this one. So it is, we have given total 30 epochs. So see the accuracy. This is with respect to time dependent. We need to identify the difference between classical deep learning methods and advanced deep learning methods. In advanced deep learning methods, this is a time dependent. Time dependent means stock market forecasting, weather forecasting, load forecasting with respect to time. What is going to happen in next 1 hour? That's what we are going to predict. If we have the data correctly, 100% sure we can able to predict. So that's what LSTM. So how much accuracy is 92.88%. If you don't satisfy with the 92.88, even we can able to get 98 to 99, but we need to give the exact data, that is the research work. Initially, I got less one, but I had changed the parameters and I have compromised with 92.8%. From this one, what we can able to understand? So we can able to understand actual and predicted with respect to the time dependency we got. Now, the last one is a convolution neural network that is based on the images. Before going to the based on images, let us see ANFIS it has run. Oh yeah, still it is running a busy. Okay, so in the meantime, let us check about convolution neural networks. Convolution neural networks, we need data samples. That means images we need. So VLSI data here. So I have downloaded the PCB images. You can see the images here. Many images. That's why 2 GB data is there. That's why I have uploaded into Google Drive, and I will share that Google Drive link. And here you can see the images, several images, PCB. So these images, what we have to identify is there any missing hole? Is there any missing hole is there? We need to identify. If you closely look into that one, so these are all looking like correct. But here you can see missing hole. That means it is not correctly manufactured. So it will identify where is a missing hole. So like that, different images all existing. If you want to study the CNN related to the missing hole, see here clearly you can see the image here. This one. So similarly, what are the other images? We have any mouse bite is there, the images that what they are telling mouse. Next images are open circuit, short circuit. So like that. So all these images we are loading to the convolution neural networks. Where we are loading for that, I am sharing all these files so that you can save the time. All steps, libraries, what are all the libraries required, I have given. Now you can see the file. File is here, directory. User receive. Here we have mentioned the file, and it is reading that all images. See all the images it is reading. So once images, wafer images, all the PCB. So I have focused on PCB. Wafers time was not sufficient. Same thing we can able to import. So PCB I have given all the PCB images here. I have uploaded. After uploading, then I just run the code. It is running now. Just updated the libraries, total libraries. Now finally, what type of, because as it was taking time, I just reduced the number of epochs. So what results finally I got is, so this is the one results we got. So how we can interpret these results? You can see here, that's what I have given before the text. So what is that confusion matrix showing? Example here, rows true class missing a hole 0, 5, 0, 2, 5. That means out of 12 true missing hole images, the model predicting 5 as mouse bite, 2 as so like that we need to understand. So 5 indicating mouse bite. So this data where we have taken from here we have taken. So 0 indicate that there is no defect. This 5 indicates that that particular mouse bite. See here, first one is missing hole. The second one is a mouse bite. The third one is related to open circuit. The fourth one is short circuit and spurious copper. So these are the things they have given. So from each this one, so it is identifying. At this moment, how much accuracy I got? I got only 10.67% only accuracy. Why I got 10.67? Because of the time constraint as image processing, it will take 1 hour time to run the code. So I just run this code only for one epoch. See here, one epoch only I have taken. Before I tried with 10 epochs. 10 epochs itself, it's taking 30 minutes because it has to process all the images. So if you just train the system for 1 hour or 2 hours, 100% sure that above 90% you will get the accuracy. And it will identify where image processing, by seeing image, manually we cannot able to see, no, this is a small IC, right? We need magnifier glasses to check how much time it will take, but it will identify in the processing itself where it has damage. That IC part, it will not go to the customer and it will be thrown out outside itself. Okay, so like that it can able to identify. That's why we need the advanced deep learning method. This method is related to the image processing. The another method is related to the time series. The others are related to the table data. Okay, and let us see the yeah, we got. Now, when we run the ANFIS, so ANFIS can see here the output. ANFIS adaptive neurophagy inference system, one of the most popular methods. Yes. You can see the how much is the accuracy we got here. Accuracy we have got only the 46.4 because of we have not given number of neurons. It was taking more time. But you can see the results, actual one 0.97. Only this was a wrong because of that it. And here 0.95, 0.98, 1.01. Almost all, 1 or 2 only, but it's matching the actual and predicted things. So this is about the ANFIS. So what we have learned is how to apply the classical deep learning methods and advanced deep learning methods